Hi, good morning. It's very early for us too. Welcome. Thanks for being the brave ones this morning. And the three of us, myself, Larry Gritz from Sony ImageWorks, Alex Wells from Intel, and Max Liani from Pixar have collaborated to give you a little view of some work that mostly these guys have been doing to take open shading language and provide a new backend that runs on newish hardware. So we're just going to sort of briefly give you a quick view of what's going on with open shading language in case you're not already on top of that, and why, even though performance is pretty good, we might want to give it a little bit of supercharging there, and then a bunch of technical details about exactly what's going on in this project and what it says about how to program for this kind of hardware. Of course, I hope you know, shading is the part of the 3D rendering process that actually makes different materials look in the way that they're supposed to look. You know, whether it's pattern generation, how they respond to light, displacement, and so on. So it's a big part of generating the realistic looks for computer graphics. Open shading language is a programmable domain-specific language that is catering to this particular purpose. There have been other languages before, but this is unique in a couple of interesting ways. And one of them is that it's open source, and so it has since been incorporated into a pretty wide variety of products, both commercial, open source, and proprietary in the studios, and for the technical advancements as well as the wide adoption, it got an Academy SciTech Award earlier this year. So it's a little bit on top of people's minds, so it's a good time for this talk. So OSL has been used extensively in the last couple of years. I know at least 60 films that have used it for shading, and another dozen or more that are in progress. So this is adoption is growing really rapidly. One of the things that distinguishes OSL from similar shading languages that came along before is that it's really, the other ones all grew up in a time when rendering was really not the rigorous physical simulation that it is today, and it was starting to really show its age as a result. Just as a broad overview, one of the things that OSL really changes is instead of the shaders computing final colors in a view-dependent way, it instead computes something called closures, which is a little function object that's view-independent and can be evaluated, sampled, and so on later by the renderer. So it's a very different sort of piece of information that it's passing around, and so there's no ray tracing, sampling, or integration happening inside the shaders themselves, which was making shaders super complicated and hard to maintain and very coupled to renderer internals. And that separation is partly what makes OSL able to be used in a bunch of different renderers with different architectures. It doesn't have to reach into the guts quite so much. OSL shaders, rather than being these big monolithic blocks of code, are actually are organized into individual nodes strung together in a network. So each individual one is a block of code, but at potentially as late as, while you're in the middle of rendering it, at render time, the renderer can assemble these into a material network, connecting the outputs of upstream nodes to inputs of downstream nodes and make this dynamic network. And this is all expressed through an API that the renderer uses to talk to the shading system. And these shading networks can actually get quite large. I'll have some numbers about that later, but dozens to hundreds of nodes in these networks is not unusual. Just to give you an idea of what's going on here, and we'll come back to this particular example later when discussing what's going on under the hood. OSL shaders, look like little fragments of C programs. They're probably familiar to anyone programming in that sort of family of languages. There's math operations, there's standard library calls, there are variables that are local to the shader, and there also is global state that you can access, like the position that you're shading, the surface normal there, texture coordinates, that sort of thing. So the basic schema of how the system works is humans write the OSL source code. There's an offline compiler that compiles it in a sort of preliminary way to a portable bytecode. But then at render time, when the renderer is actually up and gets the scene description, from the modeling system or whatever, at that point, all the individual shader nodes are strung together and connections made, and particular parameter values, given concrete values to form the material description that you're going to use at that moment, for that frame that you're rendering. And so one of the interesting things here is we have this render time optimization that happens at a fairly late stage after all those things are known. So if you would imagine what it's like to compile the individual nodes separately, there are parameters that come in and you don't know what values those will take on. And you don't know what else will be in the material network or networks that it's part of and what will be connected. But at this stage, we actually know all that information. So we can do so much more than we could if we had, like separate compilation of the nodes in C++ or something. So most of those parameters are known. They can be turned into constants, and that propagates its way through analysis of the shader. We can get rid of all the conditional clauses that aren't taken because they're controlled by parameters that now that we know how they're set, and so on. And then we use LLVM compiler framework very extensively. We will take our post-optimized shading network, turn it into LLVM intermediate representation, run it through the LLVM optimizer after that, and then we get executable machine code that we can actually call into directly. So that should be quite fast. This is all, it's an open source project. It all comes as a library that renderer authors can use to integrate into their renderers to handle the shading. And there are two APIs that are sort of all the communication between those. There's one API that the shading system presents that is what the renderer calls to say, set up this point to be shaded. Here's how this material network is strung together. Compile it. Execute the shader on this point in this global state. Give me back the results, and so on. There's a second API that the renderer exports to the shading system called renderer services, and that is the one where through that the renderer provides all of the information the shading system might need. Asks the renderer for texture lookups, or asks the name resolution on a coordinate system name, like all those little things that it might need from the renderer itself. And so there's no communication outside of those two interfaces, and that's part of the reason that this thing can be plugged into different renderers. In our experience anyway at ImageWorks, because of this shading network-wide optimization that happens once all those values are known, we actually end up with faster executing shaders than we did when they were all implemented in C++ and compiled separately. A few words about the complexity of the kinds of scenes we deal with, just so you understand how the scalability of systems like this is really crucial. So here's a final frame from a movie that we're working on. This is actually a final composite, so it's the combination of a few different elements. There's some foreground stuff and the background stuff in midground, a little bit of fog in between. I'm going to cite a few statistics, and that's just for one of those elements. So for the frame as a whole, actually imagine that happening a few different times to be combined. So one of these rendered elements is 300 million unique triangles in the scene, but there are the vegetation is instanced, so what's really being explained to the renderer is almost 9 billion triangles. This renders with a memory footprint of about 22 gigabytes and using 16 core hours. I'm not quite sure for this particular frame what the wall clock time is, because we do run multi-threaded, but different machines have different number of cores, so sometimes it's easier for us to just kind of keep track of the total in core hours, just to have an apples to apples no matter which machine it ran on. There were 85 billion rays traced to make this image, and at that resolution that comes out to 15,000 per pixel, so that's a lot of sampling and a lot of shader invocations, so that's 173 billion calls to run a shader. There were almost 3,000 different material networks that went into this scene, and that's 237,000 of those individual nodes instanced. And if you do the math, that means that each material is actually a collection of, on average, 80 nodes, networked together in some complex fashion. So the look dev artists, can make some pretty complicated materials, and if that's the average, you can imagine that the outliers can be pretty extreme. And just to give you an idea of the size of this, also, there are 52,000 texture calls for every pixel in this image in that one element, which means 324 billion total. So this is referencing a texture set of over 8,000 unique textures, totaling 77 gigabytes on disk, but those are compressed files, so if those were all in memory at once, it would be 174 gigabytes. We have a caching scheme so that we don't hold all that in memory at once, but it's just a crazy amount of data and computation that goes into every one of these renders. So that optimization pass at runtime that I was talking about, in this case, it's really aggressive. So in this case, it took, for that collection of materials, started out as the compiled bytecode of 280 million instructions and 160 million variables, and squeezed that down to a mere 2.7 million instructions on a little less than 2 million variables. So that's 98, 99%. That's pretty good, but we always want to squeeze more performance out of this. And so on that note, I'm going to turn it over to Max, who's going to talk a little bit more about what goes into production renders, problems they face, and why we might want even more optimization than this.
Thank you, Larry. My name is Max Liani. I work at Pixar as part of the renderment team. So I want to talk a little bit of what our production renderers are. So OpenShiny language take care of an important portion of the rendering, which is like shading. It drives texture lookups, but it's based on it need to be integrated in a render. And what we call production renders is this like big machine that takes all the large complexity of assets, geometry, texture, shaders, lights, jams it all together, creates a picture out of it. And those numbers are pretty common in production. So we have like these huge data sets, we have like incredible amount of texture files and long rendering hour to resolve something that often is not very what is given to the render is not often very efficiently described. Artists have very little time to optimize their assets, to do a computation that is minimal, and it also have some interesting characteristic given the type of versatility that is required. It's not a machine that is heavily optimized to do one very specific thing. They need to be versatile. Scene need to be descriptive. The user only wants to do something different, something peculiar. They need to be scalable from like very, very simple setups to like very, very complex scenes. And a traditional way to leverage the hardware that we have available is to use multi-threading to break down the computation into separate units that can be executed in different cores, in different threads. But two things are changing. One is the demand, like the scene complexity is getting more and more every year, like more pronounced, but also technology is getting it changed. Not only we have higher core counts in the machine that we purchase every year, and that is introduce a problem of like scalability and how efficient are extracting the performance out of these large core count machines. but also wider SIMD. So like a few years ago, like the SIMD units, so these vector units that were capable of computing multiple, like the same instruction across multiple pieces of information, were 4 wide. Then they became 8 wide, and now, like this year, they are like 16 wide on CPU. So are we adapting to that technology to take advantage of it? Because it's pretty important. And so some production renders are vectorized, meaning that they compute batches of points. Like I work on RandomN, and RandomN uses short vectors, like so mid-size vector actually, like so, like on the hundreds of points. So it tries to batch things together to leverage SIMD, but also data locality. So that when we intersect an object, we don't intersect it with one ray, but we intersect it with many rays. We sort them so that when we execute them, we have a chance to run the same shader on hundreds of points. And it has always been like that historically, and even recently with the RIS patch tracer. And other renders are like that. I know about Disney's Hyperion, which goes to the other extreme end of the spectrum, where the render processes large batches of like tens of millions of arrays for other reasons other than SIMDs. So in the render side, there is this extensive effort to leverage the hardware, both in terms of multi-threading and vectorization. And one of the response for vectorizing shading language execution traditionally is well, traditionally, at least recently, is to use C++ shaders because they are like relatively easy, but not that easy to write. So it is easy to write a C++ shader. To write a C++ shader is a little bit more cumbersome, but still doable. So you can have like the network of shading nodes that execute in a SIMD fashion, and you can get the performance out of it. But these C++ shaders, or especially those next or C++ shader, they lack all the like rich runtime optimization capabilities that open shading language can do. And they also lack the whole shader optimization. So a C++ shader is compiled and optimized statically. It gets deployed as like a DSO or is built into the renderer. And when the user combines together in shading network, there is very little chance to do optimizations in and out of those nodes. And also the lack of portability, which becomes very important these days, where multiple production companies, they're called together to work on the same visual effects project, and they have to share assets. So you tend to do very minimal things that makes a shader network special. So in one side, we have production renderers that have to solve the problem of increasing complexity. And if you kept up with the publication, you've seen that in recent years there is a very large number of papers that proposes different models to improve ray tracing traversal. So ray tracing gets substantially faster, and as a consequence of increase in complexity and increasing shading complexity, we see more and more that the runtime of production rendering is dominated by shading instead of ray tracing. And open shading language is a great system to reduce this shading complexity to the minimum active code path. So if in one side we have C++ shaders that can do batch execution, you can do good use of the vector units like at any width that we have available, and they are somehow easy to debug because we have standard tools to attach to it, breakpoint, GDB, or profilers like Intel VTune. But on the other side, as I was saying before, they cannot remove that complexity of the shader. For example, like if you see in this image here, this is the classic place to the node in Maya. Is available, like is often in every shading network. It appears right before every texture call, and more often than not, this use just the standard like default parameters. It's just there because the UI creates it. Maybe you can have one or two parameters that are not default, like the rotate frame. You can have like a bit of rotation, a bit of an offset, but even though these are constants. And a C++ shader will execute all of these. Perhaps it will execute conditional. Instead of rotating and computing sine and cosine to rotate the coordinates, it will check is rotate frame value at 0, then skip this extra computation, still conditional to be executed. While open shading language will identify that all these are constants, and it will fold away all the chain and turn this whole shader into pretty much a no-op, pass through the input value, which is great. But OSL in the opposite side, if in one hand we have like great optimization that the open shading language runtime can achieve, in the other hand, there are scalability limitations in terms of OSL can do like very limited execution right now on SIMD hardware. So at the moment, open shading language can do block vectorization. So it means, for example, like computing one vector at a time, or like more so like for expensive function calls, they were optimized to trying to compute the four element of a color or multiple octaves of a noise using SIMD, but that is limited to only 4 wide, which is pretty much now phasing out in the hardware that we tend to use, which is 8 wide, and soon is gonna we're gonna start adopting like 16 wide SIMD. So we have a missed opportunity here. To take open shading language to the next level, because it's a language that it is JIT compiled at runtime. We can get it to generate SIMD instructions and combine the both world, where we have a shading language that both optimize the runtime and also it executes efficiently in the new hardware. So we started this project like about a year ago, where we partner with Intel and leverage their expertise in compiler technology and in vectorization to take this project and improve it further. So I'll pass it to Alex Welsh from Intel.
Thanks, Max. Hi, I'm Alex Wells. I'm from Intel, and we're going to take a look at what it would mean to get OSL vectorized. So we're going to use a single program multiple data approach, and our main point is we don't want to change the OSL language. We don't want to make the shader writers doing anything different than they're doing now. And we want to leverage all those existing render time optimizations that Larry was talking about. But we are going to have to create a new way for the renderer to interact, to submit batches. And we're going to have to create a new backend to generate LLVM vector code. So sounds easy on the surface, but there's a lot of devil on the details, and so we'll get into some of those. So coming up with the wide interface, we prefer, the shading code would prefer to work on the ISA definition of the width, so 4, 8, 16 at a time. Often the renderer might have larger batches, and to get this project up and going, we decided just let's start with 16 and work through all the issues and come back to that and play with the batch size and see how it goes. So it's sort of a compile time option to choose the width you want to target for your batches, and the renderer can just create more or less batches depending on how you decide to set that up. So for people writing renderers who work with the OSL system, basically once you've set up your shader network, and that's all the same way you build your shader networks. But when you go to actually ask the shading system to sample a point for you, you populate this shader global structure. And it has position, normals, and all of your lovely state information about the point you want to sample. And you hand that off to the shading system and ask it to execute. And afterwards, when you want to get your results out, you can ask for symbols of output parameters from that shading network and get the address to it and then access the underlying data. So to make this work in the batch world, we just sort of replicated that interface and added the word batch on to the end. But the difference is, instead of a single shader global state, now we have multiple, and we have a new data structure, shader globals batched, to handle that, which we'll get into in the next slides. But once we've submitted a batch, now we have multiple results to access instead of just one for each symbol. So now, for a given symbol, you can get a batched accessor, and that's going to give you one of these output accessors, which is type specific, and you can use an array subscript just to access the 0th through 15th element of a specific type. And we'll see an example of that later. So the shader globals, we needed batch version, and examining the different shader globals, there are several that seemed like they'd never change over the entire life of the batch. So we split those into sort of two groups here: uniform shader globals and varying shader globals. And the shader globals batch just has both those data structures. Turn on the laser pointer here. So in the shader globals batch, you can access the uniform section and populate it how you want. And then for the varying, you can access a proxy on top of the next varying slice you're adding to the batch. And so you can access varying and then assign the position, the normal, derivatives. You can assign all those things, and once you're done assigning a particular sample, you can commit that varying and just move on to the next one. And eventually, your batch is going to fill up. And at that point, you're going to want to submit it for execution and get a result. So it's like queue-like interface that you build up a batch. So how do we represent the varying data under the hood? Well, inspired by techniques from the Intel SIMD data layout templates, we create wide wrappers on the existing data types that are already being used. So we already had vec3, matrix 4.4, float, many others. And under the hood, we have these wide wrappers, which are fixed size structure of arrays. So they're very SIMD friendly for the compilers to work with, but not always so easy for the developers to work with. And that's okay, because we also have proxies which can push and pull, import and export wide data back to the original vec3 matrix and 4x4 data types. So as a user of this, you just work with the existing data types and add it to the batches through these proxies. So under the hood, it's a little complicated, but it's pretty easy to actually use. And it provides this transparent array of structures access to the underlying SOA data layout. So when working on a renderer, sort of the flow changes a little bit, because instead of pushing one sample at a time, now you need to build up a batch. And we won't go into all these details because it's pretty small on the screen here. But basically, you have your shader globals batch. You can set up what's going to be uniform about it. So in this little expanded view here, we can see it's accessing the uniform section and assigning the render state, the array type, anything else that might be uniform for the batch. And in this case, actually, it's accessing the varying and assigning the shader to common data member as uniform. So even though it's a varying data structure, varying portion of the data structure, it's going to go ahead and blast this one value across all the data lanes. Now you have a number of samples in your batch that you want to work with, and so for each sample, you set up the varying portion, and this little exploded part here shows, great, we can access the varying, and here we're assigning the U, the V, the position, based on that sample. And once we've assigned everything we care about for the varying data, we can commit it, and that just sort of moves on to the next varying item in the batch. Now eventually, your batch is going to get full, or you're going to run out of samples that you want rendered, and you can just ask the shading system to execute that batch. Afterwards, you can use the symbol batch accessor from your symbol and get back this proxy object, which you can use the array subscript on here to actually get your original the data type you're interested in. In this case, a vec3, and then store the result however your renderer wants to use it. You can then clear the batch and repeat the process until you've processed through all your samples. So this is one of the, so you don't have, we didn't change the shading language itself, but as a renderer using this will have to change, would want to change how to the new batched interface, and it would have to change their flow a little bit. So now that we've submitted a batch to to OSL, we're going to need to try and process it in a vector manner. So we're going to use this single program multiple data execution approach, and I should call it like single shader multiple data in this case. And we're going to emit LLVM vector types directly, and part of that means we're going to have to add the logic to manage per lane control flow divergence that comes up. But there's more to OSL than just the JITted code by LLVM. All those library function calls, there's some 400 different variations of them, to like noise, absolute value, smooth step. Those are actually not JITted. They're actually implemented in C++, most of them, and we're going to need wide versions of those that work on our wide data layout that we have going on. And then we're going to let LLVM generate the actual SIMD instructions versus emitting native instructions ourselves, and that'll let us target multiple instruction sets, AVX, AVX2, AVX512, and so on. So one of the things we had to do to get going on this was switch to LLVM 4.0 from the previous 3 point something it was on to get the new AVX512 instructions. In particular, most of the LLVM intermediate representation supports operating on vectors of 16 floats at a time. Another thing we had to do was work on trying to identify the what variables in that control flow are uniform and which are varying. And we can mix and match in operations by promoting uniform values to varying when they're used in an operation with another vector value. We also had a lot of data alignment issues to resolve as the data layout we're creating in the C++ side, we want to generate JIT code directly against. So we need all those sizes and layouts to match up in between the two. So identifying uniform versus varying variables. So external library function calls are not a concern as they would be with normal languages. So in this example, there's this call transform, that's a library call. There's this call noise, there's this call ABS. So those are all library calls, and with like in a language like C++ where you can pass pointers around, you really don't know exactly what a function is going to do with that pointer. It could do anything. With something like OSL, what these library function calls actually do is very well defined. So we know exactly which things will be using varying and which ones are uniform and how that affects their return types. So in doing this, we can sort of start by assuming everything's uniform across the entire batch. However, we know portions of that shader global structure is varying. So in particular, this variable P comes from the shader globals. We know that's going to be varying, so we can trace it through all of its operations and know that the result of transform will be varying. So this point P shade will be varying. This P shade's used in this calculation of noise, so we know we need to call a version of noise that's varying. We know his result is varying, and so on. So we can actually identify exactly what needs to be varying through the entire shader, and not just the one shader, the entire network we can follow the flow through. So in particular, in this example, we can see there's this loop variable I, and we see it's never influenced by any of the shader globals or anything that was a result of the shader globals, so we can prove that it's uniform. And this is nice because the control flow for a uniform loop is much simpler. It's just like a vanilla loop. We don't have to do any special masking. Same thing, here's this frequency value. he's never influenced by anything varying, so we can just do a uniform operation on him rather than a vector one. So handling divergence. So if we have a conditional check, or a piece of code that's a conditional, if we're doing it 16 times, we're going to, a conditional gives us a true or false back for its result. So we're going to have 16 true or false results. And we can basically treat that like a mass. So when we execute the conditional, we get 16 true or false answers back here. Now, what we can do with that is we can execute basically any branch code rather than skipping it if we wanted to. And what we'd end up with is we'd have an original value for a symbol, and we'd have a value that was assigned to that symbol or created for that symbol in a branch. And then we can use the select operation with our mask to produce a result that's basically blending of the original value and the value that was assigned in the branch to store the result. And so that's how we can basically use these masks to correctly handle control divergence. But we're going to have some way to come up with these masks when they get nested. And it's much more interesting around control flow, for loops with early return statements, breaks, continues, and so on. So we're just going to look at the if-else case as a simple example. So what we do here is we keep a stack of masks around, and this is sort of at code generation time when we're building the code up. We know here's our conditional here, that's going to be our first mask that his result of that conditional is going to be the first mask we keep track of. There's another conditional, so when we push it onto the stack, we actually and the result, because to execute this line here, we have to have p sub 0 greater than 5 and p sub 1 greater than 5. And then we move down here to another conditional, and that gets pushed on the stack. And eventually we start unwinding. We hit the end of this code block here, we pop off the stack, so now the mass stack is smaller. We hit the else, so we have to push the inverse of this conditional onto the stack, and so on. So all the instructions that exist inside of each one of these blocks know exactly which mask they would need to use when they're assigning their results. But do we have to actually execute everything masked? And it turns out the answer is no. So we have an analysis step here where we basically, every time there's an assignment to a symbol, we track what the logical mask was from the stack. Then, every time a symbol is read, we look at the, so down here, G is read. We look at the writes that happened to G previously and see if the logical mask at the point of reading is a subset of the logical mask when it was written to. In this case here, G is written inside these conditional blocks, ends up being a different logical mask than outside of those logical blocks. So we know we're going to have to actually do masking on this assignment and this assignment. Here, result RGB is written to. If we get to the end of the function, because it's a output parameter, result RGB, there's an implicit read, and we apply the same logic and see that the logical scope, that logical mask is different than when it was written to last, so we'll have to go back to that last write and make it masked. But if we look at this here, we now only have three assignments we need to mask, and all the other little local variables or math going on can happen unmasked. In particular, this call to smooth step doesn't need to be masked, just the assignment of his result onto G needs to be masked. So we do some analysis here to try and minimize how many operations we actually have to have masked. One of the things we needed to be able to do is actually see the code we are generating. So we enabled profiling and debugging. with LLVM4, and actually turned out most of all the hooks already existed in LLVM. We just had to do a special build of it with one extra define here, this LLVM use Intel JIT events. So once that's been built, you can then use LLVM's debugging system, and from OSL's point of view, that means we had to add the line number and the module where the JITted code was coming from, but then LLVM tracks all of that. And then once it gets JITted, we can now profile it. We can map the OSL assembly to into vTune, and with some extra work, we could even probably get it working in GDB. So just sort of an example of that, here's that same shader. After being JITted now, we can see it in vTune. And we actually go to this source line and see the assembly associated with it that we got from JITting. So now that we can actually find where the JIT code is in vTune, we can actually come in and take a look at this. So this _2 is the actual name of the function that's JITted from that marble shader we're looking at. And we can see actually it doesn't take that much time. However, it turns around and calls that noise function. That's a OSL library call. And we can see here that OSL noise function, and this is not JITted code, this is library code, is actually taking 95% of our time. So even though, you know, we might get this nice SIMD JITted code, we need all those library calls to be wide in SIMD and do well. So let's take a look at the wide version of the noise. So there's a bunch of different noise versions of noise: Perlin, uPerlin, Simplex, Cell, Gaber. And those, many of them, were already using block vectorization, which basically means if it happens to do something on X, Y, and Z, it goes, oh, look, I can line that up in vector lanes. But again, that's only X, Y, and Z. That's only 3 data lanes being used. So we want to make a data parallel version, because now we have a batch. We actually can run the noise algorithm side by side 16 times. Now it's complicated C++ with a bunch of hashes, lookup tables, gradients, and the approach we used here was to use explicit vectorization of the outer loop using the OpenMP 4.5 standard, which the Intel C++ compiler supports very well. And one of the things we had to do was revert the code from this block vectorization, which was using intrinsics, just to regular C++ algorithm. So it's sort of like going back to where it started. Then we did some other hand tuning to improve its performance. So sort of before, here's this operator. It takes a vec3 and produces a floating point result. And basically it calls this Perlin function, and that was implemented with intrinsics. And here's our new version that works on 16 at a time, or in this case it's a templated parameter, so we can do a bunch of different sizes. But basically we have our vec3, but it's a wide accessor to them. That's one of those proxies. And here's a wide accessor to the result, which is a float. And so again, we use the array subscript to access the individual data lanes and get back to the original vec3 type, or to assign a float to it. So we just have a loop that walks over the data lanes, extracts the original type, here's a vec3, and just does normal C++ code here. So it's just going to call the Perlin scalar, which was our sort of intrinsics version of the Perlin code. So inside this Perlin scalar, he doesn't know anything about vectorization. He's just doing a scalar algorithm. You know, very vanilla C++ code in there. But because we have it in this loop, we're using the Pragma OMP SIMD the compiler says, great, let me just do this on 16 data lanes at once and generate AVX512 code, and just marches through it and does all the hard work. And produces some strikingly good results for any of the different instruction sets you might ask of it. One thing to maybe note here is you might look at this and go, well, if your data is in that wide SOA data layout, in this vec3 that's AOS, are you paying a conversion overhead? And the answer is no, because if all of this is inlined, the compiler can change this data layout. And if we look at the optimization reports, it'll actually tell us it's making a private version of variable p as a structure of arrays in the C++ code here. So it'll be loading a wide vector to a wide vector, and there is no transformation overhead. Yet all the code worked just like regular AOS code. So the trick there was getting everything to inline so the compiler can prove that it doesn't need to maintain the old AOS format. If you were to call a real function call, it would have to have the AOS format around to pass that function call. But when everything's inlined, the compiler can prove nobody can get at this local variable except me, so I can change the data layout however I want. And it just does that all automatically. To make sure everything inlines, I'm using this pragma force inline recursive, and that basically tells the compiler, I don't care what your heuristics say, everything in the next code block, inline. Because it's always an option whether a compiler is going to inline something or not, regardless of what the language says. It's just a hint. So this just takes that out of the compiler's hands a bit and tells it to do it. So we're able to generate some really good code out of this and get an idea of this using the Intel Advisor tool and taking a look in the original version here. This is too small to read up here, but this is that noise function here, and looking here it tells us that it is using SIMD code, but it's only using the 128-bit XMM registers, which are 4 data lanes. And we can find that _2, which is the JIT code of the marble, and we can see there's no SIMD instructions identified. Now in our after version here, in our batched version, using our wide version of noise, we can see it's using 512-bit ZMM registers. We can see it's using fuse multiplied adds and subtracts, and the wide version of _2 is identified as using AVX 512. So looking at the finish line for this particular one, the JITted code is 13.2 times faster in AVX 512, and the noise function is 4 times faster. Why not 16? Because the previous version was already using 4 data lanes. So we're going from 4 to 16 data lanes, so the maximum possible would be a 4x speed up on that. So to sort of combining those two speed ups and looking at some results here. So for that marble shader, the overall speed up running from test shade, which is a harness that ships with OSL, is 4.2x faster. Moving to this oak shader, which is more complex, has some loops with breaks and other fun stuff in it, is 4.8x times faster. This particular pattern here is a 3-node network. And it's using a lot of noise functions and layering them, and it's getting around a 3.3x. And we move on to a really much more expensive shader network for this procedurally generated shading of this statue. And it's using a very expensive Gaber noise function that was not block vectorized. So in that one, we're seeing a much larger speed up of 9x because the starting line was scalar. But to bring it back to reality a little bit, what would happen if, these are little, small test shaders? What if we took an entire production character? So taking a look at the shading network for the Fillmore character for one of the diffuse channels on it. It's about a 300 node network with 191 layers, and it's using a ton of texturing. Now we haven't made it to the texturing subsystem yet to widen to create a SIMD version of that. But with everything else just going on through the batch system, it's running about 1.4x faster. So we're hoping when we get to working through the texturing system, this will come up quite a bit to improve that. So our next steps are trying to do our covering all the built-in library functions. There's quite a few variations. We're going to work on optimizing the generated code and looking at all the mask management code. and how that's generated. We want to experiment with different batch sizes. And we want to explore the SIMD texture system, as well as looking into maybe splitting shaders up into different stages around these expensive texture calls. You know, and at this point, wanted to open it up to questions. Don't be shy.
Is this on? Yeah. It depends on the renderer. Some renderers just provide their own texture system. Most of the renderers that use OSL use the texture system that comes with OpenImageIO. And so that is the one where we are simultaneously trying to make a fully vectorized version of that. And very similar to the noise functions, that texture system already has the four-way, SSE-based vectorizing inside the individual calls, but that approach, that's like, because most texture lookups are either 4 channels or 3 channels, so that worked nicely for a 4-wide SIMD approach, but there's not an obvious way to scale that to 8 or 16. So as we speak, we are in the process of trying to overhaul that to add API calls to that texture system that ask it to shade a batch of 16 points or whatever at a time, and then the SIMD approach will be to process those in parallel rather than to try to do the sort of block vectorization on individual lookups. So anything that ends up using that texture system will benefit directly from that. For a renderer that completely supplies its own, to get sort of the full throughput that we hope to get out of this, they would need to do a sort of a similar overhaul of their texture system. And for that matter, this all has to happen on the renderer side too, right? So like, you won't get nearly as far with any subset of renderer, shading system, and texture system, still being serial. Like this kind of needs an overhaul on all 3 fronts so that they plug in so you stay serial the whole time, and that's where you're going to get the big speed up. Yeah.
So you just said the results we expect to get. Have you done any back of the envelope calculations for when you have the 16-wide or batch texture lookups of what you expect in production from the production shading?
Well, no, we don't have numbers on it yet. Again, we hope to get like a 4x speed up out of that part because it's already pretty decently, using the 4-way. Like, it's hard to tell, but there's also ways that we can sort of exceed that because, there's a certain amount of per overhead that happens that is, on each call now that will turn out to be only happening in 1/16 of the calls, right? Because the batch is all going to be looking up from the same texture, right? So from the renderer's point of view, you don't just take 16 rays that could go anywhere in the scene and run it through. Like you're basically sorting it, so you're getting a batch of 16 that's the same material using the same texture. So there are various kinds of overhead that the 4-way, vectorizing now doesn't take any advantage of at all because it's still an individual lookup for each API call. So when we move to doing 16 lookups for each API call, like we may even come out more ahead than we think, but we don't have numbers to put to it yet.
It also depends a lot on what type of texture you use within your shading network. Like, for example, if you're using a color for shading the albedo or like a vector displacement, then yes, there is vectorization done on the multiple channels, but a lot of texture are single channel, like bump, scratches, masks, and all of these do not leverage almost any SIMD at the moment. And as Larry was saying, if at the moment, like, for example, like from Renderman, we have shading batches, and we execute, we were executing open shading language inside a loop. So execute shader, extract the result, execute shader, extract the result. And for example, if we were to use OpenImageIOS texture system there, what happens is, because every shader exercise many texture lookups, you might have, in some of our assets, we have like 200 texture layers. So even if there is like a pretty decent per thread micro cache for like reclaiming the same texture tiles that were just called in the previous shader, because you go around robbing, you pretty much end up in the worst case scenario where nothing is in the per thread cache, execution after execution. Like this, if you just call, like after properly sorting the batch so that they are like relatively coherent, at least at the texture level, it's like, oh, I'm going to do 16 calls on the same texture. I'm going to do 16 calls, and this will stress much less the per thread cache and resolving the file name and all those things. So we expect results from there.
So how big is the overhead between the SOA and
So how big is the overhead when doing SOA to AOS? So let me see if I can back up to the slide here. The short answer is inside of like this noise function, the overhead is 0 because we never actually do the conversion. Because we got everything inlined, the compiler is able to create an SOA version of this vec3p. And he sees he's loading it from this array at unit stride. So it's able to load 16 X's and put it in a register or the stack. 16 Y's, 16 Z's. It's able to do that, and there's 0 overhead. If this wasn't vectorized, or you called a function where it could not create that version of P, it can still vectorize and do 16 things at a time, but now you're going to have the overhead you're talking about where it either does wide loads and a bunch of shuffles to fix the data layout, which the compiler's very capable of doing, or it'll have to do 16 individual loads to put them in the right spot for the AOS data layout. So this is, it looks to the programmer like AOS, but if you follow our recipe, there'll be 0 overhead for that. Probably more of the overhead is on the populating side. When these white structures need to get populated by the renderer, chances are that's not going to be in a SIMD loop. But it's not really any much more overhead than if you were having to build up an array of structures for these things. You still had to move these individual scalar values to another place in memory. So I think that overhead would be similar. So
that means the overhead between the render side to the OSL for the SOA AOS version for backend course is very small, or a couple percentage, or 10%, or 20%?
Yeah, so it depends on what you have in your render. Like in RenderMan, we already have the data in the appropriate layout. So actually, we were incurring into overhead of going the other way around to calling the non-SIMD version. So now we already have the data in the right layout for the batch, and we're just like doing like a SIMD move instructions to populate those registers and calls. So we even have less overhead than we had before. But if let's say your render, all of your points are scattered and it requires a gather operation to populate that, you might incur into a little bit of overhead. So if your shader is absolutely trivial, you might be able to measure that. But in the middle of the rest of the render, I doubt that it's going to incur like a visible penalty, especially because you're calling the API, and those are often like virtual functions. You're calling the API fewer times. So it's kind of like a recovery from that.
yeah, and just to, I don't know if I can share a number on this, but from our early integration, the overhead to pull results out was an order of magnitude less when measured with timers for a production render.
I understand this is an Intel I wanted to ask about why is there no GPU-related jobs here? Like, why is it not implemented in the GPU?
Yeah, repeat the question.
So why this is a CPU-specific talk and not there is no GPU-related data in this talk? I'm aware of a separate initiative where like something similar is being done to run on GPU, but it's not something. It's sort of like a different talk and like a different, like slightly different techniques.
This is done on the CPU for, let's say, historic reasons, or that's the current implementation?
Because no one's made a good GPU implementation yet. There is a GPU. NVIDIA is similarly helping to make a CUDA and optics-based back end for OSL in a project that's not dissimilar to this. But historically, OSL has not had a GPU path at all, and partly that's because none of the high-end renderers that use it particularly care. Because it's just an extremely difficult problem for GPUs to do, and like on a good day, going downhill with the wind at their back, like the best GPU ray tracers are maybe a factor or two faster than a good CPU ray tracer, and so having like a totally separate code path, it is like we all want to do it. And it can be extremely hard to justify it on empirical grounds just because it's not as magically faster as people think.
Especially when you start using like 60 wide instructions. So all of a sudden, if you before, like the comparison where, you know, like non-particularly well vectorized code or vectorized to somehow to 4 wide SIMD to like some GPU code that is like refactored to be wide, and you get these numbers of, oh, like this factor, like 5x or whatever is thrown at you. Often these are not necessarily like apple-to-apple comparison. When you start using proper simplified code, you see the difference is not that much. And one of the big differences is not even that, is the fact that on CPU, or at least like traditionally CPU production renderers, what is given to the renderer to work with is like order of magnitude more complicated than what you see in the like a GPU demo, where you have hey, this is one texture for the diffuse color, one texture for specular roughness, that's it. And here we're talking about like some of the assets that we get from Pixar. Like we tested so that like blanky spotter with like that one. So let's repeat that. That 1.4x is because we intentionally excluded the SIMD of the texture lookups. So when the shader execution arrived to call a texture, we loop over single point execution for texture, because the work is not completed and we didn't want to put there like a mixed information. So say that is an example of what happens if you don't vectorize your texture lookups. You get, but still with that, we get like a significant speed up, but you don't throw away a 1.4x.
Yeah, like
so,
you know, I mean, a good thing to keep in mind is remember that the jungle slide that I showed earlier, you know, that was 174 gigabytes of texture, you know, referenced in that scene, and that's not big. Like we don't think that's big at all. And so, you know, what's the biggest GPU memory you can get? 16 gigabytes or something if you really splurge. So, like, we're very frequently dealing with scenes that there's just no way to cram it on a GPU to get into that. You know, like GPUs are really good at the things they're really good at, but once you need to start paging things on and off disk in the middle of your render, like they stop being good. And so that's the kind of thing that has kept most of the really high-end production, you know, studio renderers from being GPU based, is we just don't know how to scale it to the size scenes that we want to do. And so CPU is what does it for us.
And you could argue that artists could do a better job of optimizing their assets so that they don't throw like at the render things that are this big. But like that shader there, we couldn't put an image there because we didn't get approval from production. But that shader was 300 shading nodes just to drive the diffuse color.
There's 78 other.
Even I think that's crazy, but yeah.
That's kind of like a crazy end of the spectrum, but that's why we wanted to put it
Yeah,
like
no,
there and say.
no, the stuff like that happen. It's crazy, but stuff like that happens in production all the time.
So don't underestimate what this like new 16-wide processor can do.
Just one more thing. This is one thread results. If we look platform to platform, you know, our latest Xeon Gold has 112 threads available that can be, you know, working on this as well. And that threading is handled usually at a higher level in the renderer. This is just trying to get that extra multiplier on top of hardware that it was already around, in at least to going to AVX, AVX2, that's already there, that you know, the studios want to take advantage of. Okay, yeah, some more questions? Yeah.
What are the absolute times of these numbers? Would this be suitable for basic, if you wrote for very basic shaders, would this be applicable for real-time shading?
Sorry, could you repeat your question, please?
So ignoring the unoptimized Nintendo touches for basic shaders, would this be applicable for real-time?
Yeah, I mean, like, you know, from our point of view, it's the same code that executes if it's, you know, a 6-hour renderer that gets, you know, sent off to a compute farm, or if you're watching it live in front of an artist's workstation and we try to make that as interactive as possible. It's the same code path, so as far as we're concerned, if we get a 4x speed up, that happens across the board.
So these numbers this could easily calculate real-time versus shaders.
You can do real-time application. Yes.
Yeah, I mean, you could talk about the statue.
Yes, so that statue there, we could render that at a like reasonably high frame rate, and you wouldn't accept the result as real-time rendering because of the noise of the path tracer. But if you will do some other form of integration where you don't use Monte Carlo integration techniques, the patterns underneath, so open shading language, will run like at several tens of frames per second. So yes.
So, any more?
All right, thank you for coming.
Anybody here that knows nothing about AI and that's why they attended the session? Okay. Well, hopefully we can get you started. Do I need to wait for a signal at the back, or?
Look for Stephanie in the orange shirt.
Okay. So there is a handout. Those of you that have the handout, you have an opportunity to, we're going to share with you a couple of innovation tools. Okay. So welcome today, Mark. I'm Esther Baldwin. This is my colleague, Mark Kaczmarek, and we work for Intel Corporation. We're going to share some of our opinions and things about artificial intelligence and why we believe it's the next evolution for usage opportunities in graphics and VR. Now, obviously, we hadn't attended the conference before we put this together, and now that you see what's on the exhibit floor and what many of the other topics are, we aren't far off. So we're going to give you an introduction to AI, share some innovation tools, share what life is like with AI for graphics and virtual reality, how Intel can help you move to AI, and then we'll use the innovation tool so that you can tell us how you can use AI where you're coming from. So AI is moving into every industry, but it's not new, even though there's a lot of buzz around it right now. It's, you know, at least 80 years old when it first started being talked about. And when computer scientists started working on it, in the 80s, I have friends that got degrees in it, and now it's only between 2010 and 2012 that there were breakthroughs with algorithms that are enabling the current fourth revolution. People like Andrew Ng at Google, allowing advanced image searching and categorization. But data analytics, everybody has heard of, and that is moving up into artificial intelligence, and I'll show you why in just a second. But businesses are increasingly using data to sense, reason, act, and adapt. And those that aren't should have a wake-up call that we're at a transition point. But it really began with analytics. It began with, you know, big data and people wanting to get insights from their big data. And this is what the analytics curve looks like. It starts with descriptive analytics, moves up to diagnostic, predictive, prescriptive, and cognitive. And as you start getting to those dark buttons at the top is when you start getting into machine learning and moving up into artificial intelligence. And the kind of things that would happen on that curve is, you know, all the way at the bottom, it's hindsight. Well, what happened? Are you still working in spreadsheets? Because that's where you are on the analytics curve. You start to get insight, what happened and why, and then you start to get some foresight, what will happen when and why. And then you're able to make some decision making. If this happens, then do this. And then you start to get more computerized human thought simulation and actions. It's a very large category all on its own, and it's a vital tool for reaching higher maturity and scale for data analytics. And what we're talking about really is advanced analytics, not operational analytics. So when I said it's moving into every industry, are any of you here in government or academia? So it's already being used extensively in government and academia for national research, fundamental research, security, simulations, astrophysics. How about energy, oil, or gas? Anybody here from energy, oil, or gas? Financial services, manufacturing, life sciences and healthcare. You can read as well as I can. You can see what the usages are in these existing industries. And then we get to media entertainment. It's being used for richer experience. It's being used with avatars and bots. You've got VR plus AI with training. It's being used with graphic design and in theater. So we're at a technology transition. And every technology transition is a disruptive force. It's an opportunity for great riches or the perils of not adopting quickly enough. And here's 3 examples. Kodak invented the first camera in '88 for the everyday person, invented the digital camera in '75, produced it in 2003, but filed Chapter 11 in 2012. Nokia, #1 mobile phone brand in 98. I bought one of their phones in 98. Developed touchscreen in 2000, and then in 2013 sells their mobile device businesses to Microsoft. Amazon becomes the internet-based retailer in 94. In 2015, surpassed Walmart as the most valuable retailer in the USA. 52% of Fortune 500 companies have disappeared in the past 15 years. So AI is the fastest growing workload in the data center. This is what it looks like in 2016. And 91% of those loads are running on Intel architecture. And you can see that there's Intel architecture plus a GPU, which is about 7%, and then other is 2%. And so that's why we're interested in helping other people be enabled in the AI space. So here's, you take it further deep down to where the potential for disruption is, and here are the other industries and what the usages are in those industries for artificial intelligence. And I've only highlighted 3 of them in what people might be most interested today at this conference, which is advertising, education, or gaming. So the message that we want to communicate is change before you have to, that AI is coming, and we believe that AI can be used for good. It will help you meet your goals faster, and it will help us scale ourselves as individuals. And we believe that we need machine learning, AI, data analytics, so that we can sense, reason, adapt, and act to meet business and customer needs, and free ourselves to make more time free more time for the creative process and less time with repetitive and task-based work. If any of you are doing repetitive or task-based work, that's a prime opportunity for including either machine learning or artificial intelligence. So it's another game changer for graphics and VR, but we'd like to introduce what is AI, and I'll ask my colleague Mark to help with that.
Good afternoon. I'm Mark Kaczmarek. I wanted to let you know a little bit about what is artificial intelligence. So, as Esther had said, artificial intelligence is a very old field. However, because of the advent of great compute capability coupled with massive amounts of data, we've seen a great resurgence in artificial intelligence. So it actually is a field that is still evolving and adapting. So really describing it at any one particular point in time is going to be changing, but at its core, artificial intelligence is about machines mimicking the cognitive abilities of the human mind. And there are many ways of going about this artificial intelligence. One in particular is this one I have here, which is using data in massive amounts to create a network that makes decisions. So we call this deep learning here in this area, and that deep learning technique runs on a neural network of some type, and this is inside what we call the machine learning. So this is a fairly simple topology, but this one is probably the most likely one that you'll be seeing. And as I said, the whole aspect is grabbing tremendous amounts of data and processing that through some very powerful compute engines. So where are your sources of data coming from? They could be machine-generated sources of data. It could be a mechanical machine, it can be a digital machine, say a simulated environment of data. It could be human-generated, and boy, humans generate a lot of data today. I mean, my daughter takes a picture like every 10 seconds and sends it out to her social network. And of course, that's being shared among all those servers. So all those servers, all those companies in the social sphere have all this tremendous amounts of data. And then there's business generated data, and anybody who's got a business today knows how much tremendous data you can get in just from your customer base, the intelligence from your competitive situation, how the environment is changing. So these are all sources of data that people want to get their hands around. So machine learning. So there is a classical form of machine learning that took a set of parameters that you determined, some limited set. So you may say, hey, I know how to do facial recognition. And I go, I know there's a space between eyes, and there's a distance between there and the top of the mouth, or there may be a area of the entire face. You take that limited set, you plug it into a formula that you've created with certain weights, and then that allows you to classify the individual. In this case, Arjun Bansal, he is our software algorithm head, scientist lead. He runs our team there in artificial intelligence. And so if you took this classic model, it comes out and say, hey, Arjun. There's a new method known as deep learning. Here you actually had to, as I said, pick those parameters. What were those parameters? And do you even know what those really specific parameters are? In many cases, we don't know the best way to pick a parameter. So what we've done is we've created deep learning. Deep learning takes the same raw data, it feeds it into a network that we call a neural network. This neural network then determines what are the key parameters. It's done in the network itself. So you feed it data, the machine itself, the compute, picks out those specific key parameters and then trains a model. You can then deploy that model, and then that model will say, hey, it's Arjun. So in this case, you'd have to know, but here, you may not know all the parameters, and the machine, the artificial intelligence network, determines the proper parameters. So deep learning, it takes features that are discovered in data, so the deep learning network discovers that data. It extracts the key features. You don't have to extract them. It extracts them. You actually get more performance, better performance with more data. So you can see where in this current environment with massive amounts of data, especially like cloud providers and stuff, have all this data, even businesses, all this data, they have all that data now to start putting through a network to actually training and finding those key parameters. And it gives you a degree of precision and power that was not possible before. So it's not just image data or audio data. You can now use much more complex data, say time sequence data, or even video. So deep learning, the real breakthrough happened in 2009. In 2009, a Stanford research team took image data, and they found that by using graphics processors, the high parallelization possible there, they found that they could improve the reliability or the image detection dramatically. And you see, since 2009, on image recognition, we have now approached the point where we've crossed over the human ability, actually as good as humans in image recognition. The same thing has been used on speech. Once we hit this, this point of the neural network capability, which is what we now call deep learning, you see a dramatic improvement in performance. Taking massive data with mass compute and get great performance. Now, this was before the advent of highly parallel processors. So this is where GPUs were originally used. But now, with the advent of highly parallel processors from Intel and our Xeon line, you'll see even much more dramatic performance in artificial intelligence.
So you saw a list of some of the models under machine learning. There are so many different types of models, but you really do need to have a mathematical aptitude in order to become a developer in that field. Some companies are now making it easier for people so that they don't have to have that mathematical aptitude. It will present the model for you, and what you have to then have is your data. But the biggest, some companies say that 90% of the challenge is cleaning the data in order to process it through those models. And so if I were to encourage anybody to focus upon, what area do you need to focus on, it would be looking for those companies that are helping people to clean that data in order to process it through the different models that are now available, because you no longer have to be an expert in order to use these tools. But what I thought I would do first is introduce you to some innovation tools so that you could look in your industry and predict and plan what is going to be next in your industry, so that we don't end up like a Kodak or some of the other companies that have missed these transitions. And one of those innovation tools is there's always increasing automation. It does not matter which tool or product you look at, there is increasing automation. And this is a simple example of the sewing needle. It goes from a tool, they add a transmission, they add an energy source, they add control, and then it becomes smart. And that's at that smart level is where you need to ask yourself, where is my product, or where is the company that I'm in on that curve? Because you can skip. You don't have to follow this evolution. Here's another example of innovation teaching us what's coming next. So things start with a mono system, a bi system, a poly system, and then it becomes combined. And this is a really simple example. There's hundreds of examples of products out there where this is what happens in the product life cycle. And then the next one is the evolutionary trend, where things go from being non-movable, they're immovable, and then they start to move, they end up with joints or many joints, and I'm using the door example. Then you end up with, it becomes very flexible or elastic. Then things start to move into the liquid and gas phase, and then you end up with a field. And I promise you, you can apply this to almost every single product or process or area that's available. So just look at glasses, for instance. They started out with single vision, then double vision. As you get older, you need multiple visions. And then somebody decided that they were going to add a gas and make that a flexible lens. And then you started to see Google Glass, and you end up with what we've got in the VR world today. And so you can use mathivation to decide what can you do, where can you apply IA, Intel architecture, to deliver AI, artificial intelligence. And you can add, so what can you add? Either something that's the same or different. So when we talk about VR or graphics plus AI, you're adding two things that are different together. And you can add them in either the content creation stage or in the consumption stage, where somebody's consuming the graphics or the virtual reality. Or what can you subtract? What can you take away or shrink or trim? What would you no longer need if you added AI? Where can it be divided or separated? And then the consolidation and simplify principle is all about AI in and of itself, because businesses are increasingly using big data to extract insights. They're shrinking down what they need to know. Another example would be system on a chip. Or you can reverse the flow, rotate or pull. So these are really simple brainstorming technique for you to decide where should we add AI, or include AI, or replace something with AI. Here's another technique, which is reapplied innovation. It's the same idea or a new context being applied somewhere else. So here you see superglue. During the Vietnam War, they couldn't process injuries fast enough, so they started supergluing instead of stitching. Brought that back to the US. The backpackers started carrying superglue around with them. The medical companies added an antibiotic ingredient, and you've now got an entire new market and a new industry at 1,000 times the price of a superglue package. Same with computer-aided design. You know, it started with the likes of MIT and a British man using it for architecture, and then it moved into the automotive and aerospace industry, it moved into the military industry, it moved into the semiconductor industry. Unfortunately, it was purely 2D at entry level there, and then you're seeing it in the movie industry, and it fueled the growth of CAD companies. So you can look at where can you reapply things that are already invented or existed in order to get growth, and AI is one of those things. So here's the addition. What if I add one more? What if I add another one and another one? And so in graphics, you've got the story of it started out with pen and paper, people added templates, then you had CAD and engineering applications, FMEA, solids modeling. You get into the graphics world and they add bodysuits, plus, you've got rules-based automated schematic capture. But if I just look at the bodysuit, it's not hard for me to know, based on the evolution of innovation, what's going to come next for that bodysuit. It's not going to be a bodysuit that you put on. It's going to be something else, a field that detects the movement, or perhaps a projector that locks onto the body and projects the points onto the body, and then a different one detects the movement. So you can use this technique to predict what's coming. So here's a usage model. I think it's more powerful to share usages. This one is AI is powering rehabilitation. So somebody who has movement, they're handicapped, disabled for some reason, you can put a wearable or a sensor on them and you can teach the system, how can this person move today? Why were they injured? What part of them is injured? And then you can use the fool the brain neurons with VR, because the VR does not know that the person is disabled, but the brain activity level has gone down. Let's say somebody can't move their legs. The brain activity level has gone down. It stops communicating with the legs. The brain says, they don't have any legs. I don't need to communicate with them. You put them in VR, and it fools those brain neurons, and it thinks, oh, he got his legs back. And they can start to move again. And they're using extensive physical therapy, robot exoskeletons to help those people. Well, that's not scalable. So how can you scale that into this community? You add AI to VR where you sense what the movement is, and then you create a feedback loop. You provide haptic or digital content feedback in order to encourage further movement. And who would be who in that usage? You've got the clinician, the doctor, or the research platform, and they're taking aggregated data from the partner company or the edge to help with decision support and treatment protocols. You've got the content provider or the company that came up with this idea and is then delivering this service out to the disabled community, and then you've got the users themselves. You can use it for pain management and phantom limb therapy. Phantom limb therapy, people can't unclench a painfully unclenched fist because they don't have the fist anymore. But the brain doesn't know that if you put them in VR and you tell them to relax the fist. And if you start detecting which content or what has worked, you can start to create that data lake that will help other people. And you can start to use that. You can use different touch options because the brain has two sets of neurons, touch and pain. And that's why you see TENS units downstairs, where you can buy a TENS unit and it will deliver touch, and that disrupts the pain neuron so that you don't feel the pain as much. The same thing can happen when you add VR plus AI. Treatment for PTSD and other therapy. So VR is being used to help people with post-traumatic stress disorder. This isn't new. It started in '97. Dr. Skip Rizzo at USC Institute for Creative Technologies is quite famous for this. If you add AI by using an avatar, it can interact with the veterans and ask questions based on veterans' responses. And the studies actually show that veterans feel more comfortable talking to an avatar than they do to a clinician. And they're also, the novice clinicians, they need to learn how to help people that have challenging clinical problems. And AI creates virtual patients using voice recognition to teach new clinicians those interviewing skills that will help them become better. So you've probably all heard of Stanford University's surgery simulator that has haptic feedback. So if you use the addition principle, Currently, there's no smart instrument or sensors in the operating theatre to gather that real surgical feedback. After they've received their VR surgical training, how do you then include real feedback into an AI model in order to improve the surgical training from the beginning, or even add, as what everybody has heard of Siri, add a digital assistant to the doctor in the hospital. So if you look at the theatre, even the theatre is not immune from adding AI. The Royal Shakespeare Company partnered with Imaginarium and Intel to add augmented reality into the theatre. And so this character in The Tempest is, the entire character is displayed using projectors onto the stage. But we all know that in theatre, things don't usually go perfectly every time. Anyone who has been in theatre knows that you like to play practical jokes on the other actors. Sometimes they'll hold the stage door so they can't open it and get off the stage. And so that's why they teach actors how to ad lib. You have to be able to go off script and act off the script. And that's real people adapting in real time. So if you add AR, if you add AI to this, then you can get real-time natural language processing to understand that the script has changed and one of the actors is ad-libbing, so that the projection doesn't go on top of what the actor is saying. The avatar can self-adjust. You end up with real-time rendering of the new avatar and new audio creation. Now, real-time rendering of the new avatar, that's no simple job. So I would invite you to go to the Intel booth to see the ray tracing demo that's being done down there at incredible speeds. Facial animation. You use AR to do better emotion sensing and training, creating better facial animations. You can take that one step further and reapply the innovation of the digital assistant, and now you can say, I've now got a lip-reading digital assistant because we've already trained this AI model how to perfectly form lips for speech. Therefore, you can also read it back. I talked about the downstairs for rendering. We're calling it software-defined visualization. So we're supporting a community effort for high-performance, high-fidelity, in-situ CPU-based rendering. And it's an open-source community. And the two tools that we have used, I'm going to show you the data for Embry, but I'd encourage you to go and see it because it's not beyond belief when we say that you can do, that we're approaching a time where technology will allow that the speeds that are needed. So this is a path trace render. This is the performance showing Embry versus NVIDIA. And these are the different, you can see the different software that's used. And the configuration details for this are in the final slides, just in case you want to see how the configuration was set up for this. So you're starting to see massive amounts of performance at the CPU level. If you add AI to VR shopping, you end up with better recommendations. So think about the targeted advertisers that appear on your streams today. I speak more than one language, and when I write in Spanish to a friend, I start getting all Spanish ads on my Facebook. If I speak in Mandarin, I get all Mandarin ads on my Facebook. And so they know that, there's access to all of my photographs. So with VR shopping, the algorithm may have access to all your previous viewing patterns and see what you're wearing and see what colors you prefer. And so it will only show you things that have long sleeves or plus sizes, or you have a preference for blue. So VR shopping is, it's kind of scary, really, if you think about the data that there is access to. Here's VR training. Everybody has seen VR being used for training. So if you add AI to that, you can start matching students with the best handheld device based on data. Maybe a tablet's not good for this student. Maybe they need a phone. Maybe they need a better coach. You can match them with a better expert. You can even start to do black box analysis of the equipment that's being trained. We've done it on a robot. We did black box analysis of the robot. And you can train the robots in VR. You can use it in architectural design. There are systems that provide the first blueprint based on the architect's design specifications. And it includes organizational design optimization from their AI organizational design application. The first blueprint is automatically local building code compliant. In the game environment, complex storylines instead of the programmed limited decision options. The player can engage with the environment and not just the other players and objects, and players are paired based on their ability. The weather adapts, the lighting adapts, the texture adapts, the objects, many more elements can be interacted with. Think about Star Trek when Captain Kirk beat the Kobayashi Maru. He reprogrammed it. What if the Kobayashi Maru had sensed that he had reprogrammed it and adapted back? With game characters, no one player has the same experience as someone else because both the environment and the game characters adapt. You've got different roles from the best to the worst player, the best ethics to the worst ethics, and you can start to do player matching. There's no more cheating with books that share how to win and how to find hidden objects, how to open and progress to the next level. And here's AI in animation. It can analyze, and you can see the pictures of we've got a gorilla here. Oh no, it's a chimp. AI could be used to analyze the gait, the speed, the bounce, hair movement, limb positioning, facial expressions. Feed that through a deep learning algorithm, and you end up with more realistic animations. Audio, language localization. It builds a fast, accurate animation model linked to the script or the storyboard. With AI, design life is easier. Designers can enter their parameters and the system automatically generates multiple first articles the designer can adapt, freeing time for the creative process. Go take a look at what Autodesk is doing. They have a prime example for this. No more searching through endless files for that one image you know is there and you want to reuse. I've cut and pasted a picture and I've placed it, because I'm in a hurry, in the middle of the file that I currently have open, and I can't find where I put it. No more checking local government rules and regulations for compliance. The design becomes correct by construction with AI. Now you can do a lot of this with rules-based, but it's not going to learn as things change. And we all know that the business world and things change. Local government rules and regulations change constantly. Image searches within non-tagged libraries become instantaneous. Automatic archival film location and restoration. Modernization of existing footage. So let's say your favorite TV show, they had all of those big hairdos, and you can now go in and re-engineer all of those using AI. And you could create a new Charlie Chaplin episode that is indistinguishable from the original. So AI with Intel is the next thing that we'd like to share. Don't forget that you have to have the data.
So how is Intel participating in the area of artificial intelligence? Intel has definitely positioned itself to be a leader in artificial intelligence, and we do have a unique set of assets and skills to compress the innovation cycle in artificial intelligence and deliver new products and services to the marketplace. In particular with Moore's Law, we'll be able to deliver industry-leading performance, efficiency, and density at industry-leading cost effectiveness. So independent of what you're looking at, let's say you're doing big data or maybe predictive analytics or maybe even deep learning, all these different types of AI solutions, we do have a full portfolio of products and services and tools to enable you to be successful in that space. We are not a point product company. So we are really looking at what it takes to deliver an end-to-end solution for all of the IA space. I know I've been talking about deep learning here in particular, but if you look at all of IA, we do have products and services for machine learning. We also have areas here for reasoning systems, which are another element of artificial intelligence. We have programmable solutions, FPGAs, that you can actually program yourself to get best performance. We have computer vision solutions, Ovidius as well as RealSense. We have tools, software capabilities available. We also do memory and storage solutions. We have networking available, and we also do communication. So when I'm saying end-to-end, we really do have all the aspects created, or all the aspects necessary to create your artificial intelligence solution. So in particular, in deep learning, we are bringing out a set of products that are designed for IA right from the get-go. In particular, in the deep learning space, our Nirvana technology-based solutions are designed specifically for neural networking applications, and we are leading the evolution here of AI with scientists that are working on breakthrough technologies and innovations, delivering new solutions in hardware and services. We have the ability to help our customers scale those solutions all the way from, say, an embedded solution all the way to a data center, from a small company to a very large company. We are looking for ways also to help our customers find those gems in their data. So there's value in your data, and we're looking for new ways to unlock the possibilities of you pulling that data out and maximizing maybe your creativity aspects or your business. And we are looking at AI and how it will impact society. So we are leading the effort, working with governments, social organizations, as well as societies on how we best can make use of artificial intelligence and the transformation that is coming forward to us. So from a deep learning standpoint, we have what we call our Nirvana portfolio, and this is the stack. I'll start down here, hardware. So most people know us from our hardware, and I'll talk a little bit more about our hardware in a moment, but this covers our compute capabilities as well as our memory and our networking solutions. We also have a large organization dedicated to designing libraries, compilers, and other tools to help you optimize your solutions for artificial intelligence. We are working with all the key frameworks in artificial intelligence right now, optimizing them for performance on Intel solutions. We have a variety of platforms that we are bringing out today, and that all lines up helping the industry deliver the unique experiences required by the customer base. As I said, we're end-to-end. We scale all the way from the data center through the gateway all the way to the edge with our Xeon processors, as well as our programmable solutions, say FPGA, our new Crest family, which is coming out, which is an ASIC for maximum performance, as well as solutions for video or visual input. So Xeon is really our most agile platform, and we just launched the Intel Xeon Scalable Processor family, processor scalable family. And this family was known as Skylake. So if you've heard of Skylake, this is the product just released last month. It built on, it's our next generation Xeon, so you can make use of all those capabilities you already have, those software programs available. So you can make use of the ROI you've already invested. The new processor scalable family has great performance versus our previous generation, so you're training in hours instead of days. And it's a production-ready solution, so designed for broad deployment. As I talked about earlier, Stanford had done their first analysis with graphics processors, but this was before the advent of CPUs with tremendous parallel capability. Xeon, now heavily parallel processor. The Xeon Phi is our family of massively parallel processing cores. Currently, we're shipping the product formerly known as Knight's Landing. In fact, Knight's Landing delivers great performance. When it came out in just months after it came out in 2016, it was 80% of the new flops on the top 500 in the November list. Knight's Mill is a new Xeon Phi processor coming out this year, and it is designed specifically for deep learning training. It will have performance 4 times better than our Knight's Landing product. It scales. It's got access to over 400 gigabytes of memory, of which 16 gigabytes are actually in package, high bandwidth memory. And this is a great product to get started with today in your investment in AI. Crest family. So our Crest family, this is from our Nirvana acquisition recently. This is an ASIC. This is a very high performance product designed specifically for neural networking deep learning training for those who need extreme performance. We're looking at 100% or 100 times a reduction in time to train by 2020 with our Crest family. First silicon is coming out in 2017. I have a large amount of high bandwidth memory in package, upwards of 8 terabits of memory access per second. As I said, you can also program, you can get programmable solutions. Our ARIA 10 FPGA, this is where you can actually program your silicon solution, silicon solution to actually make use of the algorithm that you have. This is a great product for inference where you can get a time-to-market solution based on what your algorithm is. Part of the Nirvana Cloud is the Nirvana Deep Learning Studio. You can make use of this to actually see how you import your data. Like I said, you need to start with massive amounts of data, so you take your data, you need to curate that, and with the Deep Learning Studio, you can take your data, import it in, build out the necessary model that you need, train based on that data, and then deploy that model at scale. As I said, that's available today in our Nirvana Cloud, and later this year will be available for on-premise applications. And if you are just getting started in artificial intelligence, say you don't know a lot about it, or let's say you even do know a lot about it, you can go to the Nirvana AI Academy. We've got tutorials there that you can watch and make use of for all skill levels of people in artificial intelligence. But this is a great place to start if you're looking to learn more about deep learning or artificial intelligence in general. Okay.
So let's try it. I gave a handout to you, and you saw the addition principle, the subtraction principle. What you're seeing in your handout is the way that the human brain works. When people start to brainstorm, they only focus on coming up with new ideas for about 2 minutes, and then they start moving into these other areas that you will see on your paper. So if you're interested in sharing with us, we'd love to see where you think AI can be applied in your industry, and we'll enter you in a drawing if you share that with us. But you've got take 2 minutes and only think about ideas for where you can put AI. And then after the session, go through the other stages that your brain will go through, which are the emotional, I don't think this is a good idea, or my gut feel tells me that this won't work, or there's a process that's needed to get this started. I need more information. What are the positive things about this? So you can see the first one is, what are the ideas? And very often, the data that's needed is where people get stuck on. Where do you need to get started? And so that's why we would point you to the AI Academy or other online sources for how do you get started. But this is, this method was created by Edward de Bono in Cambridge. He's a cognitive psychologist, and he says that after 2 minutes, you're going to start thinking about these other things anyway. So we'd like to end the session with you thinking of where you could apply AI into your company or your organization. And then we will be here after the session if you want to turn that in. But our call to action is today, is to start today. A year from now, you'll wish you had. Consider AI as where are you on that capability curve that we shared earlier. Examine the impacts of to your data, your business, or your AI opportunities, and plan and prepare your usage, solution, and infrastructure. The first thing anybody needs to get started is, how would we use this? What is our usage? The next stage is, where is the data that will allow us to use this? And you don't have to use existing data, you can use simulated data. So things like the generative adversarial network model will allow you to train a model, and it can use simulated data to do that. So you can find out more at the intelnirvana.com or the intel.com AI. So you can learn, explore, and then engage with us. Contact your Intel representative for help. If you have a great usage that you want help on and would like to do a proof of concept with us, come and talk to us. Thank you for joining our session today. I said that at the end of the presentation, there were configuration details for the benchmark data that I shared. And this is the configuration that we used. It's completely hard to read, but if you need a copy, we will get you a copy. Thank you very much.
Are there any
going. See if it works. Well, look at that. Tech companies and IT works. That's shocking. I don't think there's anybody else coming, so we can close that door in the back and chat away. Let Paul in. All right, it's 2 o'clock. Figure we'd get this session kind of going and rolling for a minute. So my name's Neil Bunn. I'm the CTO at Scalar Decisions. Today we're doing a session on Studio Cloud powered by Intel and some of the performance implications of some new Intel technology that we're incorporating into Studio Cloud. We're also here to make a couple of announcements related to our partnership with Studio Cloud. So I'm going to speak for a couple of minutes about Studio Cloud. If you're not already familiar with it, how that operates, what that means for you. I'm going to pass it over to Jim Brinker from Intel and the Data Center Solutions Group to talk a little bit about the trends and directions of technology and really why Intel is adopting a technology path that aligns very, very well with the things that we've injected into Studio Cloud and how that's going to change over time, so some of the coming kind of services that we'll be offering. And then we'll have a little bit of a panel discussion, the three of us, around some of the changes that we've had. We've got Xavier here from Animal Logic to talk about, what's really been changing over the last kind of 5 or 6 years, what the future probably holds in terms of being able to create dynamic and cost appropriate rendering facilities for studios while maintaining compliance with all the different changes that have been going on. So we'll kind of talk about that, and ideally we'll just kind of do a little bit of an interactive thing here with members of the audience and anybody who has some questions, because obviously Xavier has some deep industry experience, and we all have some interesting perspectives kind of coming from different areas. So to kick things off, if flipping works, it does. How many of you are familiar with Studio Cloud? Just a quick show of hands, a couple people familiar with Studio Cloud, lots of people who are not. So Studio Cloud is actually really interesting. The concept of Render Cloud, which is now effectively Studio Cloud, was started by the Vancouver Studio Group, basically a peer group in the Vancouver area, lots of large-scale studios, small-scale studios that participate in kind of a peer advisory and peer support sort of organization. And way back kind of mid-2000s into 2012 or so, the group recognized very quickly that there was an interesting challenge that all studios were facing as they bid on projects. And that really was the peaks and valleys of needing equipment. And at the time, hyperscale, large-scale cloud deployments were very difficult in terms of compliance, but the challenge being, for any studio that landed a large deal, you went out and you acquired a whole pile of capital gear, render gear appropriate to that project, and during any ebb or flow, you really just had gear that was either sitting idle or aging out. And similarly, if you needed burst capacity, you really couldn't get it. That's a really challenging model in terms of capital, and so they proposed amongst each other, perhaps they could create an exchange amongst the studios where, when someone's peak lined up with someone else's ebb, they would do some equipment move. They issued a proposal out to the larger IT services groups in the area, Scalar Decisions being one of them, around how to actually develop a site that could be compliant and able to support that. So we invested a few $1 million in building a render-specific data center facility and a site that would enable this basic community exchange to begin to come together, and that was kind of the first phase of Studio Cloud. Initially, there were kind of 3 main partners, so Digital Domain, ImageEdge, and Rainmaker kind of came together. It was about 1,000 systems to start over a 3-year period, and that has now grown to many clients in Canada and several thousand systems across the country in multiple locations. It was interesting, though, at the time, one of the big challenges was largely around compliance. You needed to use air-gapped networks. The audit regimes for MPAA, Disney, and Marvel were very unfriendly towards kind of any sort of VLANing technology, sharing of really hardly anything. And so in order to be able to exchange, it really was this rough, raw tumbleweed of people actually going out and pulling cables and wiping drives. And even though racks were maybe beside each other, you could maintain compliance and isolation between groups through air-gap networks. Kind of moving on forward, that exchange has continued to grow, community-driven. We have dozens of clients in it now across the country. It kind of operates in 3 main sites right now, Vancouver, Toronto, and Montreal. Many thousands of systems in each of those sites, shared by a great number of studios. But part of the reason we're here today with Intel is to announce a large-scale joint partnership to expand and rapidly improve those facilities and improve the terms that are able to be offered between participants. And so now people joining the exchange are able to kind of join in very short burst elements, so down to kind of 3-month periods at very, very low cost. So a fraction of the cost it would be to kind of do similar things in hyperscale cloud. And we're investing two-sided in technology, in people, and research around what this is going to look like over time for rendering environments. The contracts, as I kind of indicated, are now very, very flexible, and they're backed up by the fact that participants now have a portal and an ability to actually do cross-exchange through a portal. So even though the contract terms and when you kind of buy into the shared facilities will be kind of 3, 6, or beyond contracts, you are actually able to share, if you wanted, on a daily or monthly basis inside that exchange between partners in the exchange. So it allows for very, very flexible movement of equipment. And part of the element here in terms of the partnership with Intel is to provide a lot more float systems, a lot more burst capacity into that environment so that the exchange, kind of like a financial market, is very well populated. There's always lots of supply in terms of the ability to kind of leverage systems across that. And it also sets up the stage for an anticipated kind of international expansion of these sites and facilities. So for anybody who kind of doesn't know how it works already, you know, I've described it. It's a little bit of a financial model with a little bit of a networking model associated with it as well. So if you're a studio in any of these locales or further away, and we have clients elsewhere, but predominantly studios like to be fairly close, low latency, high bandwidth networks to it. We operate dark fiber networks and connections between the studios that are participating in Studio Cloud and our main facility. Inside that main facilities, we can handle either hosted equipment, so studios who kind of submit equipment into that facility, or through the short-term rental and acquisition models. And then we're also announcing a partnership with Conductor Technologies, which allows for that hyperscale burst, so for those very fine-grained peaking, or the ability to be able to burst into GCP or Azure as an example for fine-grained elements. But again, you know, for most of our clients, achieving a cost-effective, high-quality product really is about a blend of things you own, things you rent, and things you burst to in terms of a hyperscale perspective. And this change and this partnership with both Intel and the addition of Conductor into kind of our ecosystem allows for a complete spread across that service domain. So in terms of kind of how people actually use it, you know, most clients have an element where they believe they kind of understand their capacity to some degree, and they decide to make a purchase or a large-scale investment in a longer-term base capability. Maybe that's 60–80% of their typical render requirements. And so they invest in that, and they invest in that into the exchange. And as they hit their valleys, and this is kind of the diagram here depicts it a little bit, as they hit a valley, you can see kind of the gray where they offer nodes, they reduce their own capacity, they offer nodes out into the exchange. One of the other exchange partners acquires those nodes, and so effectively it covers that capital cost. So when you're, you know, in between contracts or in a lull where these resources would otherwise be idled and actually just depreciating assets, you recoup the finances because someone else actually probably needs them. That's the nice thing about having a sufficiently populated exchange. And then when you need shorter term bursts, you're able to kind of, you know, you're at the peak period in a project, you need a little bit more capacity, or maybe between that 80 and even 120% of your standard capacity. For a few months at a time, you'll be able to engage in the short term rental. So, you know, 3-month or even sub sub 3 month for select engagement terms. And then where you really run into those challenges, those last minute, re-renders, those engagements where you need to scale very, very effectively, you're able to go out and use hyperscale burst by way of Conductor, so long as you've pre-provisioned for it. And in fact, one of the topics we might talk about a little bit here is the nuance of using hyperscale cloud providers, when that's appropriate, when it's not, how to maintain compliance, and the challenges associated with that, which predominantly are all of this is about pre-planning. So pre-planning to be part of Studio Cloud, pre-planning your budgets, and making things very deterministic from a studio perspective, and that enables much more success financially. So as I kind of already indicated, the intention here and the agreement with Intel allows us to change and become much more flexible. Prior to this, most studios entered into Studio Cloud kind of on 1 year or greater contracts, and then just did kind of exchanges between each other. Now, because of both changes in technologies and the investment that Intel's making into the facilities, alongside Scalar, we'll be able to offer much shorter term for large scale acquisition of nodes. And then we're also working with Console, which is a direct connection provider to enhance the network connectivity out of the facilities into hyperscale cloud providers such as AWS, GCP, or Azure. So again, you've got that full suite ecosystem from end to end in terms of how you can both acquire technologies and then burst into whatever size and scale of render you need. From an example perspective, we have a huge suite of clients already. These are some of our larger clients. So we've got Deluxe and Technicolor, DHX, Jamfield, obviously Animal Logic, and others already using the facilities and leveraging the technologies that we have available. So the second question that kind of comes up for people is, why is this announcement being made with Intel? What's going on in that regard? And the gestation of Studio Cloud really was largely vendor and technology agnostic. It was really whatever the world needed, we'd find a way to kind of inject into Studio Cloud. What's really interesting, and Jim's going to talk about it a lot, is Intel's vision associated with the needs of compute and highly balanced application performance over the next kind of 5 or 6 years lend themselves, as we all know, to extremely strong performance in many of the areas that people struggle the most. And so we're investing in these new architectures. So some of the systems that we'll be adding into Studio Cloud are based on the Intel Skylake architecture. It's a next generation architecture. It has dramatic improvements in memory performance, dramatic improvements in terms of accelerator extensions, SIMD extensions, and the AVX extensions, which allow us to obtain much greater application throughput. And in fact, one of the other talks that's been performed in this room really is about how several of the large software packages, such as RenderMan or OSL, have been finely tuned for this next generation of technology. And so it's not just that you get a few more cores or you get a little bit different in clock speed. You're actually seeing large improvements, multiple times improvements from one generation to the next, because they're able to take advantage of these new features. The focus on application performance we think is really interesting, but it also adds a lot of complexity to most render environments. As I kind of indicated, you can't go in and assess a set of capabilities anymore by pure numbers of cores, pure clock speed of those cores, or the memory that are in those systems, because it's becoming a more complicated conversation. And so we're focused on enabling a balanced portfolio to always be ready. We have a team of engineers that basically are profiling and benchmarking applications against these nodes to be able to very quickly give guidance to clients on the nuances between those architectures and how that all works. And the last part is, Intel has a very keen understanding of systems level performance and not just kind of components and nodes. They're focused right now on improving the overall balance of that system from memory to fabric technologies such as networking, all the way through to processor technologies. And we're going to be ingesting and injecting some of those technologies, such as Intel's 3D Crosspoint technologies and Optane technologies around storage and fabric technologies, potentially to improve the overall balance of systems and and better move data around. And that is one of the struggles almost all of our clients are having these days, really is the size and the volume of data, the fact that you now actually have to move so much data between nodes. You can actually run into bottlenecks even on 10 gig networks. So 40s and 100s start to become things that, if they can be done cost effectively, become very, very attractive to speeding up and improving the overall efficiency of the system. So a couple of things that we've found already when we're kind of evaluating some of these new technologies that are going to come into our site. And the challenge that we always have as engineers and anybody who's kind of designing compute farms, it's really easy, as I've said a couple of times, to kind of go backwards and just think in terms of my total amount of storage and a couple DIMMs here and a couple DIMMs there, the number of clocks, gigahertz that I've got in my base CPU. But it's really important to understand that as we kind of move into the Skylake and Purley architecture, that a number of those things change. The number of memory channels, for instance, changes kind of from 4 to 6, and anybody who kind of remembers back a couple of generations remembers, some of the Westmere and Nehalem systems. You ended up with these odd, memory configurations. We're all kind of standardized on these kind of 8 gig boundaries, right? 64 gigs, 8 gigs, 16 gigs, 32. That all broke way back in a 3-channel world, and so you started to have these odd things like 24 gig or 48 or whatever to maintain memory balance and obtain full performance. Skylake adds that back into the mix. So it's a 6-channel memory architecture design. And so making sure that you're actually achieving all of the bandwidth, upwards of 220 and beyond gigabytes per second into the memory across a dual socket system requires you to kind of rethink those memory layouts. And the second part to that is that we're learning very quickly is, gigahertz isn't gigahertz anymore. It really depends which sections of the chips you're actually accessing. And so, it's very easy for people to, without educating themselves, very quickly just stare at the specs on the main page and say, okay, this is a 20-core, 2 gigahertz processor, and kind of do some quick math. But if you actually are going to enable things like the AVX extensions and some of those elements for things like RenderMan and their optimizations, you rapidly realize that there's a different frequency that the processor operates when it's heavily using those instructions. And so finding proper system balance depends now on understanding more than just the cores and clock speed on the main spec page. It actually understands a lot. You have to understand more about the processor architecture and then the application flow. So one of the benefits of Studio Cloud and our team is that we will sit and help our clients engineer and understand both your pipeline, the applications that you're using, and help guide you on the best way to achieve the highest performance for the lowest possible capital or rental outlay inside those systems. So basically help tune the environments appropriately for your pipeline and the types of codes that you're using. And then the last part, that really plays into things is, as people start to explore into hyperscale burst and move from home, we are seeing, the need for deterministic behavior of applications, and operating applications on different processor architectures does, despite the fact that everybody kind of says binary math should be the same on all things, it actually does change things. So anybody who's really run large-scale simulations or anything that is computationally intensive on different processor generations, even from a single manufacturer, can find that things behave a little differently. Differences in rounding, differences in how a fuse multiply add operates from kind of one generation to the next. Our standardization on Skylake and Intel technology helps with this as clients start to look at hyperscale bursts, because these are the same technologies that are being standardized on for those burst workloads. So for example, as we're acquiring and putting in Intel Skylake into Studio Cloud, Google with GCP is also one of the early adopters of the Purley and Skylake systems, and so applications will perform very similarly between Studio Cloud type nodes and then GCP nodes without the need for trying to understand why there's a different behavior or different output for very computationally intensive operations, whether that be kind of particle physics or ray tracing or any of the other very computationally intensive operations where some of these nuances in architecture come into play. So as I kind of indicated, we've got a few things that we're also working on from a futures perspective inside Studio Cloud. We're analyzing our fabric and our network very, very closely. We've certainly seen, and we have a very large HPC group at Scalar. We certainly know the benefits of some of these new fabric technologies, one of which is Intel's OmniPath technologies that they're heavily invested in. And so we're experimenting with that to ease the bottlenecks in large-scale data movement, right? So large package movement onto local nodes and accelerating that, and I think Jim's going to talk a little bit about how kind of system performance improves through that. And we're working on hybridized environments, so environments that will work better in a containerized environment and allow workloads to move around both between kind of our classic on-prem nodes that many of our clients always have, into the Studio Cloud render nodes, whether that be short or longer term kind of acquired nodes, and then out into hyperscale, again, using container technologies and the other technologies associated with that, at the same time ensuring that we're able to maintain compliance the whole time with the applicable standards and whatever the SLAs and the guidance are for the various studios that are participating. So I'm going to hand it over now to Jim to give you a quick perspective on Intel and their technology roadmap.
Thank you, Neil. You know, we lost this crowd at just the wrong moment. They came in with your slide that said, why Intel? And now they've left before I can answer the question, so it's going to be tough. But as Neil mentioned, my name is Jim Brinker, and I run worldwide sales for a new division of Intel. It's the Scalable Data Center Solutions Group, and hopefully that'll make sense when I'm done with my talk as to some of the things that we are doing, where we're focused, and some of the changes that have taken place at Intel. I've only been at Intel about 18 months, and this is my first SIGGRAPH in probably 7 years. So before Intel, I was at SGI for a number of years, and I started out at SGI running the media and entertainment group for SGI as they were really kind of getting back into that business. So those historians, I looked it up finally, it's the TESRO. I was the right there at the right time when we were moving those things out into Hollywood like popcorn to all of the right places going forward. And before SGI, I was at Sony Corporation in the broadcast division. So been to a number of SIGGRAPHs. The change here is dramatic from when I left, but it is very good to come back. So my talk today is going to take a little bit of a different tone from where Neil was going, but it's going to meld right in with it in terms of a little bit of backdrop of the market dynamics that have led to Studio Cloud. Now the more that I understand it, the more that I see what its capabilities are and where it's going. The market dynamics really feed this, and it's not just happening in media and entertainment. It's happening in oil and gas and financial services across the boards, and I'll talk to that. Then there's an intersection of the technologies that really lead and intersect, and the technology changes that are taking place, and then how Intel is addressing all that. And then hopefully at the end, just really sum it up with Scalar and Intel together and why this made sense as an investment for us in this partnership. So this is something that you've probably seen in various forms, but it's really the flood of data, the data wave, whatever they want to call it, it's coming. And there's various examples of that, whether it's internet traffic or autonomous driving. You can even bring this home into media and entertainment. As I mentioned, if you take my history lesson, you're dealing with I was at HD, HD was a big thing, then you get 2K, then 4K, then 6K. This is all data that's coming out at us. It's also exploding in terms of workloads. So it's not just one workload, whether it's the Internet of Things or business analytics or AI. All of these things are really driving this data, but then there's a complexity to it that's coming forward as well, and it's something we have to deal with. These are some interesting facts along those lines that, again, if you just look at it and kind of sink in, that the CEO of today is really focused more on the digital transformation than they are on anything else. And the evidence has really come out that that's what's happening, across the boards in various industries. The other thing is that the workforce is getting younger. the millennials are hitting this workforce. They're very comfortable with this, and that's only going to increase this rate of change that we're all dealing with. And with that change, there becomes bottlenecks, there becomes problems. So, there's 3 areas that we really look at that need to be solved as we're trying to solve this big data explosion. One is the network and system bottlenecks, whether it's memory, I/O, storage, resiliency. All of those things are major issues that you've got to overcome. The second is the divergence of it. Visualization, HPC, big data analytics, or AI, all of those things are diverse, and that's causing bottlenecks within that. And then there's the cloud. And the whole dynamic around the cloud and the barriers to entering it and the barriers to usage and the barriers of the hybrid model, which again is what Neil talked about quite a bit as you're looking at it going forward. And then just to make it a little bit worse, within that is that this is really just the beginning of this revolution. If you look at autonomous driving as an example, they're saying by 2020 that will be mainstream. That'll be the norm as opposed, and that's only 3 years out. So it's kind of hard to deal with that reality coming our way, but you can see across the boards it's coming at us. So now kind of pivoting off of that, what has Intel been doing about it, and where does this all kind of come together? And we've really taken an overall systems approach to the architecture. So as opposed to just the processor, as opposed to just the compute, we're looking at the memory, the fabric, the storage, the software element, and trying to draw all those things together and see where we can optimize on top of that. The other is the codes that are out there. So whether it's our own codes or whether it's codes that are in the industry, really trying to say, how do I get from here to there? So it's one thing if a company, a CTO can shut his company down and bring it back up in 2020 with the new codes, that'd be great. They can't do that. So how do we transition from one to the other and move forward? And those are areas that we are looking at. And so bringing it all together, and Neil did a good job of describing Skylake, but when you really start looking at what Skylake represents and where we're really going, is much tighter component integration. One term that I like is, what used to be a rack is now on a board, and soon it's going to be on a processor. And when you start looking at it from that perspective, you get benefits, benefits in bandwidth, latency, density, cost, and then reliability. Another one that was brought up yesterday that I agree with is security within this. So the tighter you can keep this thing, the more secure the network you can have, and as opposed to really dealing with security with butts in a seat or things like that, you're dealing with it from a technology perspective and getting ahead of it, which is key. So this was publicly announced about 1.5 years ago. Intel entered into a prime contract agreement with the Department of Energy to develop one of the first exascale type of systems. So within that environment, this is, you're looking at today, which today was 1 year ago. I didn't fast forward the slide. And in the future is the 2021, 2022 timeframe. You can start to see where, and I did bring it this time, where there's changes that take place. So really up in this area right here is where a lot of the technology changes are going to take place. And it's in memory and in storage, and some of the breakthroughs, Neil mentioned 3D XPoint and some of these areas, those are where we're really going to get the performance gain and the tight integration of what's going on. What's phenomenal about this is that in terms of performance, the system of 2022 will have 700x the performance of the system of today. So that really starts to pause everything and say, when that happens, what's the realm of what's possible? And again, as the DOE will say, it's a point. It's not the end goal. So once you're able to do that, what can you then take off from that? And that's where it comes down. I know it's one of Neil's themes as well. It's the applications that really count. So from that perspective, if you're able to do that, you've obviously got science that really takes off at the national labs or in other areas tied to this. But concepts of like a hypersonic jet design that you're kind of seeing in the paper and hearing people talk about, right now, it's a physics problem. Everything would melt today if trying to go at a hypersonic speed, so you've got to start at zero. The only way to do that is some of the compute power that we're talking about out there. Within movies and entertainment, You know, you look at some of the breakthroughs and some of the real dynamics that are taking place, I'm sure that you're dealing with in terms of just the flood of data and the need to burst into it and the need to keep going further and further and further with what they're doing at some of these lead studios. And you're going to need more compute and more power. And you don't have more space and you don't have more power to do it. So that becomes the problem that we're all trying to deal with as you go forward. In healthcare, you know, there's a heart project that's being done right now where they're really breaking the heart in all these pieces and getting at some of the root causes of a lot of heart disease. And, you know, whether that's that or genomics or some of these other areas, very key. Autonomous driving, a fact there that fascinated me is we're doing a partnership right now with BMW on their trials for autonomous driving. And they're putting 100 cars on the road in Germany, Israel, and the US. And every car that's on the road takes 2.2 racks of data, you know, to run that car. So from that perspective, you can start seeing the explosion that's taking place. Now, again, that's the pilot, but this is a major thing that's going to take place. So Intel's looking at both from the car aspects, but also from the data center, and then some of the smart devices that are out there. So kind of the last slide, and the one commercial that I will make is that what Intel is becoming, and you're starting to see, is we're no longer a parts supplier. You know, we've made our name, and we've really, you know, gotten to this point on being an excellent ingredient supplier, but we're moving more because we have to into a solutions type company. So we're trying to form partnerships like we've got with Scalar and Studio Cloud, because that represents a new business model. That represents something to us that's a growth engine that both of our companies and the industry can benefit from. So we're doing similar partnerships in oil and gas, similar partnerships in financial services, government, and doing this on an international basis. So, you know, we're still all in with the strategy, you know, with the products and with the roadmaps and with everything else, but this was the big change that took place at Intel. This is why we're here today and what we're representing. So with that, I will turn it back to you, sir.
Perfect. Thank you. So that was kind of the presentation section of our session. So a little bit about Studio Cloud, and really what we wanted to do afterwards was have a little bit of a panel discussion and see if there are any questions from the audience around, you know, technology trends, directions, changes, challenges, and we have Xavier here from Animal Logic. Maybe you can do a quick introduction of yourself and some of your background. Some people in the audience might immediately recognize the studio and know some of your projects. Others might not. And then maybe we'll have a bit of a discussion about how to move around and how technology has changed. And I think we just have to flick that on.
1, 2.
Oh, it works.
Jesus Christ.
Everything works in technology today.
Yes, it's lucky. My name is Xavier Dedois. I apologize for the French accent. I live in Sydney, but for the last 30 years. And I've been working at Animal Logic for the last 25 years, so I'm almost an archaeological dig. But thanks for finding me and getting me out. Animal Logic, you may have heard of a few times. We starting to be in the VFX business with the Matrix. I was shot in Sydney, and we were lucky to be involved with that. And then the next big one was Happy Feet, our first CG movie that was all done in Sydney, which won an Academy Award for animation for George Miller. And then the Lego movies are probably the one you may have heard of more recently. So that's what we've been doing. So yeah, there's been a few changes over the years, obviously, in terms of some of the challenges we've seen. You know, and I don't know if we want to start, you know, getting into some of those and why a solution like Studio Cloud, you know, will make sense for us and has made sense for us. The visual effects industry has had, you know, difficulties with schedules and crunch times and deadlines for now a number of years, and so there's nothing really new there, and you know that gave birth to, you know, a small number of very, very big corporations that would have hundreds and even usually thousands of people working, because you need to have that sort of scale to be able to respond to the client's demand in the time frame. And usually the studios, use multiple VFX houses for that. So it's really been really intense. We've been spending a lot of our time on animation project, full CG animation project. So that was quite different. I mean, to start with, with Happy Feet, it was released in 2006, I believe, and I think we started in 2002, so it was almost 4 years. I mean, there was a bit of a extended, it was not the plan. The plan was 3, but we did 4. But now the schedules are getting, way shorter. And even with the shorter schedules, which, are now maybe in a year and a half time frame, the heavy compute side of things is being compressed enormously. So, usually would have up to a year of lighting, so the heavy compute. What we're seeing at the moment is that a majority of the work that you see at the movie gets done in a matter of months, and it's, anything from 4 to 6 months. It's going in that direction. It's never the plan. But it seems to be inevitable for whatever reason, a bit like the VFX industry has suffered. There's no point complaining about it. We think that's just going to be the new model of business. And that has been for us very disruptive, because, okay, if you got a multiple CG project with, 2 to 3 of you, and you've got 1 year of high compute requirements, you can sort of plan around that and, make some decisions on how much you invest, and, sign up for space in data centers, and have multi-year view of it. The model was transformed now, where we need to be, almost as agile as the VFX houses are. And that's not going to change. So for us, it's been something that we didn't have to suffer too much until recently. But it's a new way of doing business, and we don't have to like it. We just have to be in it. Some of the traditional cloud solutions, either it's by the hour or by the year. And it's obvious that for our industry, it's you may have a by hour need from time to time, but it's neither really fitting. So because the overflow compute that you were showing, it's often you need to overflow at some stage, and the durations is months, so it's not hours or years. So I'm really happy to see someone who has a focus on our industry, and the first thing is the timing. In terms of being able to access the resources on a duration that's actually fit with our business needs. And the second part is also the machine types. So it's been difficult. We've done a bit of cloud work with AWS and SoftLayer. Google has only recently opened in Sydney. So, finding the right machine, it's better now than it used to be. But having to manage a variety of different kind of instances and all that, it becomes, okay, we don't want to do that. We want to keep it simple. So having a partner that also can provide the sort of machine that we expect is important, because it's one less thing we have to think about. And obviously we've been working on Intel machines for a long time. So. What
Yeah.
a long introduction, sorry.
Yeah, no, that was good, and I think it gives a great perspective on things. I think, you know, from my perspective, one of the things that I found most striking. So my background originally wasn't in digital media. Obviously, you know, we do a lot of that at Scalar, but my background was actually in high performance supercomputing and simulation computing, and the advance in digital effects and the demand now for highly realistic environments, or highly non-realistic, but still physically, you know, things that you can see and watch and that you can relate to in human experience that have to tie back to physics, leads us back to this challenge, as Jim was kind of highlighting, the challenges that are being faced in what I'll call kind of classical supercomputing. All the same things are applying in digital media, right? You know, in VFX, you know, the biggest challenges are, well, how do I do things like water flow simulation properly, and particles the right way, and fabrics and textures and all those sorts of elements, which actually is exactly the same as the university guy who's actually modeling, you know, graphene following on X or Y or Z scales and what's it going to do under stresses. And, you know, it is fascinating that, you know, here we are at a conference that's talking about kind of an alternative reality and visual effects for things we don't want to do in real life, but realistically, the most important part is becoming the compute to make it like real life in some way. And the challenges in systems are very much the same. So over your experience, and, you know, you've obviously been at this for, you know, a great many years. The other element that constantly comes up with our clients is a changing financial aspect, right? It's much more competitive, commoditized, and as you said, you know, there's large studios and small studios. You know, the challenge is, regardless of where you are in that spectrum, how do you create a great product at a cost-effective way? Otherwise, you're not going to exist for more than one show or two shows. You've obviously been doing it for a very long time, so you've learned the ebbs and flows of those models. Do you mind giving a little bit of a perspective on kind of the changes in financing and how that impacts, you know, how you deliver things?
Yes, so apart from driving a few CFOs crazy, because they, you know, they never get, they ask questions, but they never get the answers they want. So the challenge is actually forcing us to disrupt ourselves in terms of, you know, whatever we've done last year or 2 years ago, it's a great reference, but that's not the model. We've almost never had a repetition, okay, we can just do that again and it'll be all right. Even if that happens, there's still some significant changes along the way that's being put there. And I mean, you know, I remember when we're buying workstation at, you know, $50,000 and
that was probably from Jim over at SGI. I remember some of those.
It was.
Those were the good old days.
Yes. and the software license was $50,000 too. So you know, you had long discussion and planning about how many you're going to buy, and you know, it's very commoditized, and it's a great thing because it's grown the market, and it brings creativity to a different level, and the current cloud options are almost better for the smaller studio. The smaller you are, you know, you got no legacy, no nothing, but you know, you can access anything with just spending a bit of money, which was completely unavailable to anybody until recently. So we've seen the growth of the, you know, cloud needs really more beneficial to small people than the big people, because there was not a right fit. And for us, we've poked at it, and we've had difficulties to make it work financially, because it was always, well, if we're going to spend that much, then we might as well buy it, and we take a risk, but, you know, we got to back ourselves that we're going to, you know, keep being busy as much as possible. The ebb and flows is a problem of the whole industry, so it's you know, you've got to be prudent financially, you've got to be careful that you're not overextending. You know, there used to be a view a long time ago, you know, build it and they will come, and it's just like, you know, build it and they will not come, for sure, as soon as you finish building it. So, you know, you got to be very much with your eyes on the ball in terms of, you know, what's coming around the corner, and, you know, I mean, long term is 12 months. past 12 months, it's, beyond what we look. I mean, we've got like, multi-year plans, but they're nice fantasies, and hopefully some of it will come true. But, the real planning is on a 12-month view. So, and buying equipment is usually a 3-year view, traditionally. So, being able to adapt in that way is a good thing for us.
Yeah, and that fits exactly with kind of what we've tried to do with Studio Cloud, which is allow you to kind of adapt your acquisition model to whatever that reality is, whether you actually are in a position, a large-scale organization that can take a 3-year risk to kind of drive costs through the floor and get the absolute lowest cost on things, or if you actually kind of need to manage your capital in a different way and do that in a more short-term perspective. We had a conversation kind of come up a couple of times over at our booth about, changes in software licensing over time, being a really big challenge for people, as they ebb and scale. And I think this is kind of like the workstations, right? How have you seen that change over the last few years? And I guess the second part to that is, how do you see open source technologies kind of playing in your world, or do they play for your studio right now? We've had a few conversations with people on various ends of the spectrum, full commercial, yay, this is great. And then a few guys, we know a few studios that are trying to do things that, are entirely based on pure open source.
Yes, so it's never black and white as usual, but and it depends really what you're trying to achieve. But we're lucky that we're at the size now with Autodesk. We get to a point where we get sort of 3-year agreements and a token system. So it's easy to manage. They're big commitments, but they're commitments that we can afford, but that make it very flexible. In terms of other software, well, in terms of open source, we actually, I think it was announced yesterday, where Animal Logic has put on the open source platform a bridge between Maya and USD, so the universal scene description that Pixar put out there a year or 2 ago, and try to define something that's going to be useful across all the facilities and how we describe a scene and what elements we want to have, which is a good thing because it's taken out from the vendors. And it's managed in a way where you can, make some changes and use it your own way and put it back. So I think we just announced yesterday we've built a Maya to USD bridge that we've made available to open source.
If you didn't announce it yesterday, you just did. So
no, it was yesterday. Sure. It was yesterday somewhere. So we do participate in the open space. In using some of the tools and participating in some of the tools. It's not the main part, but it is one of the parts that we have. And then we've built our own renderer around the needs for the first Lego movie actually. So we don't have too many issues around there, but I know you can now through the conductors and other people have access to something like Arnold, which is not very different from ours, on a more usage basis, which I think is essential to have that level of flexibility. So I think it's important that the industry keeps evolving towards the best and better people with great project and great productivity, creativity are the ones who are actually doing the job, not necessarily the biggest company or the one with the most cores or the biggest storage, because that's not what makes good movies. It's really the people behind. So it's challenging, but it's a good direction for everybody.
If I could, I think that's a real change that we've seen as well from the manufacturer side, is the need to not be the big company, but to be the flexible and able to do some of these new models that are coming forward. So whether it's embracing open source or whether it's some of the flexible financing models that need to take place, whether dark pools, flex capacity, just-in-time inventory, things that are needed to really manage through some of the ebbs and flows of these cycles, that again, it's not just media and entertainment, it's happening across the boards. So we're seeing the same thing.
Yeah, absolutely. So we're nearing the end of our time. Obviously, there's a bunch of people in the audience. I was just wondering, does anybody have any questions for anybody who's up here right now about anything you've heard or anything completely unrelated? Because, hey, they're up here and you have a microphone. You can ask whatever you want. Some great experience here. And if not, then we'll wrap up.
You made a comment earlier about the ability to share nodes in the exchange between peer groups without having to sort of go up through the sales rep.
Yep.
Does that just kick in a change order request that will still affect the air gap of the network table, or is it?
Yeah, well, and yeah, so right now, the exchange really is a kind of a change order request, and somebody has to go physically move a cable if your compliance regime is that you want it on an air gap network. What we're increasingly seeing, and this came up in conversation just the other day, is the need to be kind of air gapped or that level of compliance. That varies from studio to studio, and increasingly, in some of the kind of series level television, some of the advertising workloads and stuff, don't care as much, and so there's going to be increased dynamicism and flexibility done through automation tools there where it won't be an air gap network, but it will trigger, right, if you are moving a node between someone who needs air gap and someone who doesn't, that, yeah, it has to still involve a human. I would love to roboticize it, but I'm not quite there yet. We can't use the drones to plug them and unplug them yet, but we can automate almost everything else until that kind of final cable move, and that's kind of how the exchange works today, if you're in that model. And like I said, if you're part of a group that doesn't require that level of sophistication, then we can do it even faster and without the person. But I think when you submit an order, a big red light goes off and someone goes running, so it almost seems real time anyway. So that's kind of how it works today. But thanks for the question. Anything else? But yeah, exactly. It's a web portal that you can buy and sell nodes on. It's kind of like E-Trade, in some ways, because you really, it's not set by us. It's actually set by the individuals that actually want to exchange, right? I have inventory for offer, and ideally, I'd like to offer it for X or Y or Z price, and then somebody else can bid on it and say, well, I see you're $2 per node per day, and I raise you, 50 cents, and then you laugh at them and be like, well, I'll just do other jobs. But yeah, it allows you to kind of do that sort of exchange and at a very fine degree of granularity.
I was going to add something which is important to us. Is you touched on it, Jim, before, which is the complexity or the performance. Achieving the performance has moved from having more of the things that we use to the software and the hardware interaction, and through threading and hyper-threading and all the extension in the Intel world. If we continue along the same model that's been over the years, if you don't leverage those clever bits that are built in and use them into your software and leverage them, you're not going to get level of continuous increase in performance. And I mean, it started a little while back, especially when the hyper-threading came through. That was pretty obvious. But it's not the gigahertz anymore, completely. And for us, especially having our own renderer and a lot of our pipeline tools, having you guys involved and having the capacity to support and help us, making sure that we do leverage with our code everything we do with, the stuff you've been sweating to make as quick and as clever as possible. I'm sure you want to make sure that actually people use it. So,
right. No, it's a great point. Neil and I have talked about this a fair amount. That I think in the past it's always been about clock speed or about linpack run or some artificial measure of success, and really the measure needs to be application performance. And at the end of the day, it's how these codes are run, and that's where all of us need to spend more time on code optimization, code modernization. How do we work our way from here to there? And I think that transitional time is key. So I agree.
Yeah, we're seeing this big challenge with parallelism, right? Parallelism is is not easy, but if you have stuff that's easy to parallelize, that's great. You can take advantage of it. You know, you can use lots of cores, you can do all sorts of vector extensions, these sorts of things. But the second thing, and it's interesting, you know, is this challenge of, but almost everything in life still has a serial component in it. And you know, one of the scariest things actually in computing, and it's talked about a lot in very, very large, you know, PhD level circles, is that, you know, the serial component of a lot of codes really hasn't improved now in, you know, the better part of a decade, right? Like we all know that, you know, 2 gigahertz processors, you know, and the clock speed around that, you know, that was a long time ago. Like I think I was still in university when you could get 2 gigahertz, and we're still really just barely 3s sometimes, right? Most things are still operating there. And so it's great. You got the ton more cores, you got all these extensions, you got parallel extensions, but when you run into those serial elements like stitching elements or combining things back together again, you run into this bottleneck, and the serial component is becoming this increasing problem. And so we're working on that, and again, you know, it's a conversation Jim and I have a lot, is you may not be able to avoid that, but maybe you can speed up everything around it, so that movement of data between nodes when they have to seam things back together, or the movement of data, you know, from the memory to the processor before it bottlenecks for a little bit in the serial job. You don't want to waste any of those clock cycles because, hey, that part is becoming a dominant part of performance. And then, of course, you need really, really PhD level guys to try to take your serial component and find a way to parallelize it. But it is fascinating.
And also, you know, the increasing number of threads that we're dealing with. And we saw it with our own renderer, is that, you know, it would thread well up to a certain level, and then it would sort of hit a level where, you know,
the curl over on performance.
It needed to change, and so, you know, the guys would think about it and, you know, reverse everything and, you know, put something completely different, so different architecture and design, and that'll get them to another level. But there's not like, you know, run it once and it's going to be, you know, performing, you know, forever and ever.
You don't,
you know, we keep finding ceilings with the number of cores. That was, oh, okay.
Job
so.
security for you, though, right?
And it's not as easy as just take the code and recompile it. Like you're at least advantaged by the fact that you have your source to your render. Many people don't, right? And so we have to spend time with clients and explaining, no, there actually is a big reason you need to stay version current, and then challenge your software partners to make sure they're staying not only version current, they're using, you know, compiler extensions, they're recompiling for new architectures, and they're doing hand tuning and hand coding for some of these elements. You got that source code, so you can run that curve, so it probably gives you a good competitive advantage that, you know, lots of other people are probably quite jealous about.
Yeah, I mean, it's a feature that doesn't sell very well for those software vendors where they just go, oh yeah, you know, it's optimized for, you know, whatever number of cores now. It's a lot of hard work, but yeah, you know, it doesn't sell software. It's not sexy, so yeah.
All right, well, we're basically at the end of our time. We could fit in one last question if there was one, and otherwise we'll just wrap up and really appreciate everybody who showed up. Feel free to drop by the Intel booth over in the exhibit show floor. Scalers there, we're happy to chat with you. I think we still have a little bit of swag to give away, I don't know. And Intel certainly has a great number of really interesting demos at their booth. Absolutely worth seeing a lot of different vendors, not just kind of Scalar. And thank you very much for coming in your time. Really appreciate it. Thank you.
My name is Sven Wob. I'm a graphics application engineer at Intel and would like to give you a presentation about the Embry ray tracing kernels. That's a ray tracing library that we're developing and have open sourced. In this talk I will first give a short overview of Embry, then talk a little bit about its API and how you could use it, and then talk about some more advanced features that go beyond just using triangles. And in the end I'll also have some performance comparison of ray tracing using Embry on different CPUs, and we'll also compare against some GPU. Let me start talk a little bit about the usage of ray tracing today. Ray tracing has become a very popular algorithm, in particular in the movie industry, to compute photorealistic images. So typically path tracing is used there as an underlying algorithm. And using this algorithm, you can essentially achieve much higher image quality than with alternatives, and also get a very quick feedback when you want to do interactive lighting, for instance. Also different fields like product visualization or the automotive industry are using ray tracing for rendering. The automotive industry is a good example where they need high fidelity of the rendering. So if they want to do some prototyping of the design of a new car, they really have to be sure that what they visualize there really is kind of plausible, and that the car in the end will look like what they see. And ray tracing is a physically based algorithm, so what it renders is pretty close to the look that the final car will then have. There are also a couple of different areas where ray tracing is used. For instance, sound simulations can make use of ray tracing, particle simulations to some degree, particular forms of collision detection too. And also games are using it in some form, in particular in the pre-baking of the lighting. They have to compute some light textures there to pre-compute the lighting, and typically path tracing is used there as the algorithm of choice. Now, there are many usages of ray tracing, however, also a lot of challenges to implement a fast ray tracer. So, for instance, one is multi-threading. You need to multi-thread, otherwise you will never get a good performance out of a CPU. While that is still easy for the rendering part, you can just parallelize over your pixel. It's a lot more difficult for the hierarchy construction, where you have some nested style of parallelism. Embry uses here the threading building blocks, which simplifies significantly leveraging this nested parallelism you have at BVH construction. Second point is vectorization. Today CPUs have wider and wider SIMD units. It started with SSE, then we became 8 wide with AVX, and now we are at 16 wide with AVX 512. And it's really essential to make use of these units, otherwise you let a lot of peak performance on the floor. Also, domain knowledge, of course, is important. There are many data structures that got developed for ray tracing. For instance, different types of binding volume hierarchies with different branching factor, KD trees, octrees, grids, combinations of these. So there's quite a lot of algorithms to choose from. It's often not obvious what performs best. And different styles of ray tracing algorithms are also existing that operate on this data structure. So for instance, you can shoot single rays, you can shoot packets of your SIMD width, you can shoot bigger packets, you can work with ray streams. So it's often not obvious what the best choice for an architecture is. Then it's not just sufficient to optimize for one instruction set, let's say as a AVX for instance, because typically your software should run on multiple CPUs, and many people are still using SSE machines, for instance. So you need really to optimize and tune your algorithm for a variety of different CPUs. And that adds a different level of complexity of selecting at runtime the proper code path that's optimized. So we as a developer of a library also face a problem that different users that use our library have quite different demands of how the library should optimize, what the library should optimize for. So we have some users that really want the best performance and don't care at all about memory consumption. We have a mode to support this, but we have others, for instance, that really want to visualize very large models. And even with tens of gigabytes of memory that you can buy today and equip CPUs with, it's still a problem. People are rendering really gigantic models and care really about memory consumption. That's why Embry also has a mode to optimize in this direction. So Embry ray tracing kernels is a library that implements highly optimized versions of ray traversal, so finding the closest hit of a ray with a scene, and building the data structure that you need to do this operation. We achieve very high ray tracing performance on CPUs, and we often ask customers that integrate Embry about the performance speed up they achieved. And what you could expect is typically something in the range of 1.5x speed up to a 6x speed up. Obviously, 6x can only be achieved for applications that do almost no shading, something like amino occlusion style illumination, for instance. If you have a reasonable amount of shading, you typically have something like a 1.5x to, let's say, 2x speed up in total runtime. We optimize for the latest CPUs and instruction sets. So we, for instance, have recently added support for the AVX5 drive instruction set. We target professional rendering applications. So we talk to people and convince them that really integrating Embry into their system makes sense and can give very big speed ups, as I've shown before. For this integration, we provide an easy-to-use API. I will later give some little overview of how to use Embry through the API. And yeah, Embry is free, doesn't cost anything, and it's open sourced under a very open license. So we have it released under the Apache 2 license. So if you want, here's a link to the Embry webpage. Just go there, you can download it and play around with it a little bit. This here is a timeline of how Embry has evolved the last couple years. I don't want to go over all these different releases, and this list is even not complete. And the features to each release are also a selection of what was the most important addition there. I only want to make clear here that Embry is very actively developed. We have a quite regular release schedule and are constantly adding new features, making performance improvements, and fixing bugs. And we basically have very fast turnaround time typically for bug fixes. So if something small and you report it to us, we typically have in a week, at most 2 weeks, a fix prepared for you. Embry got a quite feature-rich library over time. However, we are still hearing from customers new features they need, so there will be more features be added in the future. So we currently support, obviously, finding the closest hit of array with a scene. This is our IDC intersect call of the API. Or you can ask for any hit along array. That's typically used for shadow arrays, for instance, where you're just interested if there is some occluder between a point and the light source. We support different types of rays. So we have single rays, we have array packets of different widths supported, and also array streams of different layouts. And yes, a single array is what most people use. However, with packets and streams, you can get some higher performance in case your application allows using them. Embry integrates high quality, but also high performance BVH builders. So if you do final frame rendering, you typically want to build a high quality BVH to get best rendering performance out of it. But if you have something like a dynamic scene, for instance, in a content creation tool, some preview window, you want to be able to move stuff around in your modeling tool. And you typically are cared about the build performance. They have fast updates on the preview window, and they are high performance BVH builders, which have lower rendering performance, are important. There are quite a lot of different primitive types that we support at the moment. It's triangles, of course, that's obvious, but also triangle pairs, which we call quads in our system, which can save some memory. We have subdivision surface support, including displacement mapping. We have different types of curves for hair support. You can have instances to build very large scenes. And there is some user-defined geometry feature that can be used to extend Embry with primitive types that are not yet in the system. So we recently added multi-segment motion blur. I will give some more details on this implementation later. And we built on 2 different open source tools from Intel. We built on the Intel's BIMD program compiler. That's vectorizing language which can help a lot vectorizing an entire rendering engine. I give an example on how to use this compiler later on. And we use, as I said before, the Intel threading building blocks for parallelization. That's most important for the hierarchy construction part. This here gives a high-level overview of the Embry system. You talk to Embry obviously through its API, of which there is a C and an ISPC version. Underneath this API, there is some ray tracing kernel selection layer, which is essentially some logic that takes the demands that you have specified in the API, such as I care about memory consumption, creates more data structures, and checks what CPU you're running on, and tries to find the best data structure in our implementation that matches your needs. So for instance, if you are on an AVX-enabled machine and care about memory consumption, we use four-wide BBI hierarchies, but if you care about performance, we enable the 8-wide hierarchy because this gives a little higher performance, but it's more difficult to fill the 8-wide nodes, so it creates also a bigger tree. So internally, Embry has different components. There are different acceleration structures that you have implemented that fulfill different needs. Different BBH builders, for instance, also in very high quality spatial split builder, but also very fast Morton code builder. Different traversal algorithms, I talked about this already. Various intersection routines, and a subdivision engine that can very efficiently evaluate subdiv patches. And this is all building on top of some common vector and SIMD library that abstracts essentially a 3-wide or 4-wide vector from the pure SIMD intrinsic, so it's quite handy to use. And we have actually a couple of projects are using just this layer of Embry to quickly get something done efficiently with SIMD. Okay, and let me give now a very brief overview of the Embry API. We are currently at the version 2 of the API and have been backward compatible now for, I think, almost 3 years. But we are currently working on a new version just because there has some legacy stuff is there in the current API that we want to clean up. There is the one or other little bug that we want to fix. So towards the end of the year, we will come out with an not backward compatible but slightly different version of the API. There's a C and an ISPC version, so you can program Embry from C or C++, but also from this ISPC language. The API is kind of an object-oriented API, so you create the objects like a scene object, a geometry object, and can delete the stuff, what you are used to. It's quite easy to use. I hope I can convince you with the example I'm showing later. And it's on a high level, so it hides quite some implementation details. You can, for instance, not choose to use a 4-wide hierarchy. We just have this abstracted away, and because we want to have the freedom to internally decide when it's best to use this data structure, and we also want to be able to change what implementations we provide internally. So if we at one day maybe come up with a KT tree is a lot better as what we have right now, we really have the freedom to do these changes. So that's a very simple example of how you create a scene in Embry. You just create a device that's kind of a handle to Embry through which different parts of the application can use Embry without interfering. And then this device is can be used as a class factory essentially to create a scene. In this example, I create a static scene that's useful for final frame rendering. And after you created the scene, you can add some geometries, such as triangle meshes. And once you have added them, you call this RTC commit call. And that's essentially the point where we build our internal data structures, which means only after that call you can start tracing some rays. And in case of a dynamic scene, you could again do some changes, but would have to again call and commit before tracing new rays. So yeah, this here shows how to create a simple triangle mesh. I think most looks probably obvious. You make a new triangle mesh call, specify number of triangles and vertices. But one thing that's interesting here, we are sharing here an application buffer, so vertex PTR and index PTR are pointing to application managed buffers. And Embry can read from these buffers, even though they have not a really standard layout here. So for instance, you see the vertex layout is here X, Y, Z, and 2 texture coordinates. And because you can provide an offset and a stride to this LDC-Z buffer call, Embry can read X, Y, Z even from this layout. And similar for the triangle layout here. And this gives you quite some flexibility in sharing data between Embry and your application, which can save a lot of memory in many cases. So this ISBC language I was talking about is some C-style language, plus a couple of vector extensions. It can simplify a lot writing your renderer. So you write essentially code that looks scalar, but is actually vector code. You will see later on. And one big advantage of it is that this language guarantees that vectorization is taking place. So if you, for instance, use auto-vectorization, you might sometimes do little changes to your loop, and for whatever obscure reason, the compiler decides I cannot vectorize this anymore. This is not happening with ISBC. If you write something down there, it's like this with Juda or OpenCL. This just gets vectorized, and you have a guarantee for that. ISBC allows you to compile for 2 different instruction sets. It's just a compile time flag. You can enable up to AVX512 support. And it even allows you to enable multiple of these ISAs at the same time. And ISBC will at runtime then select the proper code path. And as I said before, it's also an open source project, so you can download it and just try it out. So this is now an example of how to use ISBC for the rendering. If you quickly pass this code, you realize that it looks very familiar. There is essentially, it's just plain C. We see one exception of this for each loop, which is here highlighted. That's the only really special keyword that's here in this example. And this for each just iterates X and Y in a SIMD way over the screen, which means inside this loop X and Y are vectors essentially. And all these calculations here, is even though they look scalar, are all vector calculations. So I don't create here a single array. I create here from this vector of x, y coordinates a packet of arrays, and this intersect call traces this packet of arrays into the scene until we find a hit point. At this point, I check whether I hit something. If I have not hit anything, this GEMID member of the array is still invalid. In this case, I just set the background to black and continue the loop. And at this point, some lanes, some SIMD lanes might continue the loop, but others might continue down here with the shadow computation, which means some masking is required here to mask out some SIMD lanes. And that's all automatically happening in ISBC. You don't have to worry about this masking to do manually. So yeah, here I compute a shadow array now from the hit point, shoot this with the occluded function, and then if I hit something, I add the light, otherwise I have a shadow. That's this computation here. But it's quite a couple of lines of code only to get something with shadows running. So with just a little bit of coding, it's quite easy to get this cube onto the screen. So let me continue with some little more advanced features that Embry provides. So one is quad meshes. Embry supports quads as pairs of triangles, just shown on the right. So if you have a quad V0, V1, V2, V3, we break this up into 2 triangles as illustrated here. So the triangle 0, 1, 3 and 2, 3, 1 essentially. And this essentially allows us to also support mixed triangle quad meshes, because you essentially only have to make V2, if you move V2 to V3, this top triangle gets essentially a line and will never get hit. So this way you can make, also with this quad encoding, a triangle. So if you have the V0, V1, V3, V3, and just repeat this last vertex, you can make a triangle with this encoding. So most 3D modeling packages actually produce quads. So if you tessellate some patch, you typically get quads out of that. So That's why I would recommend just using chords if possible, because it gives you a couple of advantages. For instance, there's lower memory consumption because they're just less primitives. For this reason, the BVH building is also faster. But there is a small performance hit of, let's say, 2 or 3%, but that's only for the ray tracing part. For the entire application, you will likely not really notice that. We also support Catmull-Clark subdivision surfaces, and such a subdivision surface is essentially an approach to convert a coarse mesh, as you see here on the right with this cube, into a high resolution mesh by using some subdivision rules. And the resulting surface is really smooth, so the normal is changing also smoothly over the surface. And a nice property of this approach is that it allows arbitrary topology. So you can, for instance, also have something like this torus topology here on the right, and are not limited to just planar topology like you have with NURBS. And I think that's the main reason why this primitive has established as a standard in the movie industry today. So the most characters that you see in movies are modeled using these features plus displacement mapping. So the Embry implementation of the subdiv surfaces is compatible with the open subdiv 3 reference implementation. So we produce the same surface and also support the same features such as creases, the different boundary modes, and so on. Yeah, and we also support the displacement mapping on top of the subdiv surface. That's important because most content in the movie industry is today displacement mapped. We also support cubic spline curves, which are essentially polynomial curves with where you can specify different basis functions that Embry should use internally. So we currently support a Bézier basis. That's what we started with. But then we realized that many people are using the B-spline basis because it has a couple of nice properties. Because with a B-spline you can just add one additional control point and get with this one more third-order polynomial. So it is a pretty compact representation. And we also support line segments, so just a linear basis essentially. The radius of this curve can vary along the ray, and it's just interpolated with the same basis. And you can then make things like here in the bottom image that the curve gets thicker in the middle or something like that. Or you can probably make the end of the hair closing in different ways. There are two different accuracies that we support here. Typically, hair is typically far away, and you don't see the hair geometry. It's typically subpixel. This mode we support using some ray-oriented ribbons, but there are some rare cases where you also might want to zoom in onto a hair or want to use this feature, for instance, for streamlines and visualization. For this, we support also some real surface that's intersected using a Newton-Raphson iteration, which is essentially defined as a sweep surface of a circle which is swept perpendicular along the third degree curve. So our implementation of the hair achieves pretty high performance because we use oriented bounding boxes to properly bound in the direction of the hair. And this can give actually a 2x speed up compared to standard axis-aligned bounds. And we have low memory consumption as we just do not tessellate. So this higher order curves, we directly intersect them either by tessellating on the fly using this ribbon approach, or by having this Newton-Raphson iteration that directly solves the ray curve intersection. We also support user-defined geometries. That's actually a very important feature because it allows you to extend Embry in case there is some primitive that we do not support yet, but you want. For instance, some people want analytic spheres or disks, or for instance, also multi-level instancing. We only support a single-level instancing, but with this user geometry, you can also support multi-level instancing and implement this if you want by just taking an array, applying a transformation to it in some callback function and retracing the array into a different scene. Similarly, you can also achieve rotation motion blur by just letting this transformation you're multiplying it rotate with time. So yeah, there are many applications of this feature. And it's quite easy to use. You just provide 3 function pointers to Embry, just one function pointer that computes the bounding box of this new primitive, and you provide an intersect and occluded function pointer to intersect the array with that primitive or to test it for occlusion. So we support also a second callback mechanism. These are the intersection filter functions. That's a per geometry callback, so per mesh callback essentially, that is called during traversal for each primitive intersection that we find. And the callback can then either accept this intersection or say, no, I don't want this, and reject it, and then traversal will just continue as if this intersection would never have happened. And the original intended use for this was to produce things like you see on the right, that you can carve out parts of the geometry. For instance, if you want to model tree leaves, a pretty common approach is to have an alpha texture that defines when you are inside or outside of the leaf, and that's something you can do with this callback efficiently. Then it turned out that it's also useful for other things we didn't really thought about initially. So for instance, if you have trace a shadow array, you can use it to accumulate all transparencies along the shadow array just with one occluded call by just rejecting all hits inside this callback. And if you reject them all, you get called with all hits, and you can then just multiply all the transparencies together along the array this way. Similarly, you can also find all hits of array with a scene by just always rejecting a hit and but putting it somewhere into some linked list and remembering them. And some people use this to avoid self-intersection. So for instance, if you restart a reflection array from a surface, you can just check, for instance, if a hit is the same primitive that you originally hit with a primary array, and this can help you reducing, being more robust with by avoiding self-intersections. So multi-segment motion blur is a feature that we added recently, and it's actually so the motion blur is the effect that when you have motion in a scene and the camera shutter is typically finite, that the image should appear blurred when rendered. And there are a couple of cases. So mostly the motion you care about is linear, because a fast motion, if you have a curved motion that is significant, there would be very high forces. That's why it's not that typical. So you often have only linear motion, but there are some cases where you also have a nonlinear motion that are quite important. So for instance, if you have rotating wheels, that's a case where you have very fast and curvy motion. Other examples are fighting scenes or a flying bird, for instance, when the wings are swinging. These are cases where you need have curved motions, and for these curved motions you need this multi-segment motion blur, where you just represent this curved shape of the motion using multiple keyframes and interpolate linearly between these keyframes. So the keyframes themselves are typically equidistant in time. That's also a limitation of our approach, but it's pretty common. I have not seen anything different until now. But what happens quite often is that different geometries have different number of time steps attached. That's many, as I said before, because the typical case is just linear motion, and therefore you need only 2 time steps or 2 keyframes. But if you have then a couple of parts of the scene that really have the rotation, for these you typically specify then a larger number of time steps. So it's often that this is mixed. So our implementation of the multi-segment motion blur uses a new hierarchy, which is essentially a 4D bounding volume hierarchy that stores spatial linear bounds and temporal bounds. And this way we can essentially separate objects spatially, like a standard BVH would do. And once you have separated an object, we can also reduce the time range in case the motion in the object is too complicated. So if the motion is almost linear, we can just continue normally and partition spatially. But if you have a very curved motion, it's much easier to bound the curvature when you split time. This kind of reduces and reduces the complexity of the motion and makes it better to bound. So one property of our implementation is that it's quite efficient when you have different resolutions of different number of time steps per geometries, just because you can separate them and then can reduce time ranges in the geometry. And this way we can also support longer animations efficiently. So if you, for instance, have a renderer with a high setup cost up front before you start rendering the first pixels, you could take advantage of that and render maybe a couple of frames using one binding volume hierarchy at once. So this approach has actually quite big memory savings compared to our initial implementation in Embree 2.12. I will show some numbers on this later on. Actually, I think on the next slide, yeah. So our previous implementation of this multi-segment motion blur was just computing a large number of standard linear motion BVHs to make it work, but this had a lot of memory overhead because we needed a lot of these different BVHs over all the geometry in case there was one primitive which required many time steps. And that's the reason why for some models, for instance, the Turtle Barbarian Crowd, where there's one character with many time steps and many with fewer, the old approach wasted a lot of memory, and the new approach is significantly better. There are other scenes where there is a very low variation in number of time steps, or all geometries have the same number of time steps. There the old approach was performing quite good and there was nothing to gain, so we consumed the same amount of memory here. So we knew up front that our old approach was very fast and difficult to beat performance-wise, but we wanted to have this memory consumption defect fixed. So the new approach is, for one scene at least, faster than our old approach. That's a scene which consumed a lot of memory with the old approach. For the other scenes, we are either about having the same performance or for some slightly slower, but I think this robustness with memory consumption definitely makes the new approach preferable over the old one. So yeah, we have a paper on this approach at HBG this year. So if you want to Google this, you will find a lot of details about this in the paper. We also have a demo of this multi-segment motion blur at the Intel booth. So please come by and have a look to see this in action. So Embree also supports dynamic scenes, and we have used the standard approach of using just a two-level hierarchy, in this case a two-level bounding volume hierarchy, to achieve optimal build performance. So one advantage of the two-level approach is that this way your algorithms essentially only depend on the number of geometries that are really changing. So you can have a large scene, if you change only a little bit, you get very fast updates. However, these two-level hierarchies have also their disadvantages. And this is essentially when geometries overlap a lot. And this happens actually quite often in practice. And then you get problems because where these geometries overlap, you have essentially traversed for this part of space these two hierarchies, one after the other. And in case the traversal order is not optimal, you might even have to traverse them both completely through this part of the space. And this costs performance, often up to 2x and more. It just depends a lot on the scene. You can be arbitrarily bad, but something like 2, maybe 3x is something you can often notice with this two-level approach. And we wanted to fix this issue. That's why we came up with some new top-level build approach that can help a lot reducing these overlaps. So in this approach, we essentially exploit that for these different objects, we already have a bounding volume hierarchy. So there is a hierarchy. So we asked us, can't we just kind of use this somehow to improve the quality of the top-level hierarchy that we built on top? And the answer is yes, you can. And the idea is actually quite simple. During the construction of your top-level hierarchy, you look onto the boxes you're currently building the hierarchy over. And if you have there a box that's quite large to the current merged bounding box, let's say 20% of that or something, then you just open it by replacing it with the boxes of the children. And you have the children because it's the hierarchy you have there. And this way you make these boxes you process smaller, And this in the end avoids overlap in the top level hierarchy. We also have some approach, at some point you have to stop these openings, and we essentially stop it when we have only boxes that belong to one object, and that's essentially okay because we know that the hierarchy of the object itself is already good quality. So if we only have subtrees left of one object, we just finish this tree on top of it quickly and don't open more. And this makes the BVH build slightly more expensive, the top level BVH build, just because when you open, you produce more work. That's why it obviously gets more expensive. But this is only, don't know, a couple percent. It doesn't make much of a difference. But for the rendering, it makes a big difference. As I said, it can be 2x or even more performance improvement that you get by removing this overlap. So also this, we have a paper of this approach also at HPG. So if you want to check out the paper, there are also details about this. And we have also a demo of this approach at the SIGGRAPH booth of Intel, so please also have a look. So we come to the end. I want to give now finally some performance numbers of Embry. We use a diffuse path tracer for benchmarking here. That's just because we really want to concentrate on the pure ray tracing performance and don't want to benchmark a complex shading system. We use the highest BVH build for all platforms. This means a spatial split build in Embry, and I think the GPU does some pre-splitting approach. We use Embry, the latest Embry version 2.16, almost the latest, for benchmarking, and run on a dual socket Xeon Platinum processor. This is a new Xeon machine with support for the 16-byte AVX 512 vector instructions. And we benchmark against an Intel Xeon Phi. That's actually it's the fastest one, I think, that you can get. And we compare against state-of-the-art GPU methods. So we use a recent Optics Prime and CUDA version to compare against and run on the NVIDIA Tesla P100. I think it's also the fastest GPU you can buy today. There are 5 models we use for benchmarking. A car model with about 5 million triangles, a pretty complex villa scene with almost 40 million, some indoor scene with 10 million triangles, and the well-known power plant and San Miguel scenes. So this here is the results. The dark blue is the dual socket Intel Xeon Platinum processor. The light blue is the single socket Xeon Phi. And the green bar is the Tesla P100 GPU. So one thing you notice here is that the dual socket CPU just outperforms all the other systems by quite a bit. One reason of that is the dual socket, so it's kind of 2 chips compared to 1. That's a large part of that. But even though, so this dual socket machine has slightly lower flops as a GPU, but can make more effective use of its compute and achieve this high performance this way. You also see that the Xeon Phi performs a little faster than the GPU. So no, not very much. I think it's 10 to 20%. Even though it also has a lower peak flop performance than the GPU. Okay, I think that's the end of my talk. We have plenty of time for questions, so thanks for your attention. Any questions? Yeah?
Do you have any theories about why it's performing better on CPU?
So these are quite complex models. So I think it's likely related to memory accesses. So a big difference between the architectures is that the CPU has a lot of cache. So I suppose that it can hold large part of the scene in cache and access this quickly, where the GPU has more often to go to main memory, but it's kind of speculation. It's difficult to really understand completely what's going on there. We actually have 2 different benchmarks. We also had, I think 2 years ago, we presented a different benchmark with comparing only to optics. There we had similar results. With Optics Prime, the GPU numbers got faster. I think Optics Prime has some higher optimizations. I'm not sure exactly what's going on there. Yeah. Yes? No. That is deforming. So please come to the Intel booth. We have there a nice dynamic scene demo showing on this dual socket Xeon Platinum machine a demo with 2 million moving triangles, and these can move arbitrarily, and we run this at 30 frames per second. So yeah, we support arbitrary motion quite efficiently by using a Morton code builder to build a BBH for the individual geometries or meshes, and this top-level builder I explained before to build a top-level hierarchy on top of that. Yeah, in this way you can get build performance numbers of Carsten, over 100 million primitives per second or something like that, and much more, yeah. So it's quite fast, the hierarchy construction. But you can also have rigid body motion, of course. You can have the instancing and also move using instancing an entire object. That's, of course, also possible. Yeah. No, this is all together. This is primary. So it's one primary bounce and I guess one ambient-occlusion bounce, I would guess. So just one, yeah. Up to 8. Okay, thanks. So up to 8 diffuse bounces, yeah. Within stream-like rendering engine, so it uses ray streams internally. Yeah.
The question about the API, how does different rate packing method affect the performance?
So different sizes of ray packets?
Yeah, and the new stream or whatever it's called.
So this depends a little bit on the type of rays you are looking onto. So for primary rays, and since there's not too high triangle complexity, you can get very nice speed ups when going from 4 to 8 to 16 wide packets. This can almost scale linear if the triangle density is not too high on screen. For incoherent rays, it is much lower, the speed up you get. I would say, I don't know, so if you compare single ray to ray packets, I would guess you get something like maybe 10–20% higher performance. And because it's much more difficult if you have incoherent rays to use the wide vector units. These are much more easy to use when you have coherence in your ray packets.
I'm just curious, how do you define, how each application defines how these layers should optimize, like what's the relationship to memory?
Yeah, okay. Okay. I didn't talk about this, but there are some flags you can specify to a scene when you construct it, and these flags give essentially Empree some hints of what it should optimize for. You have then an compact flag and a robust flag essentially. So this compact mode, if you enable it, we try to consume as little memory as possible. But not as little as possible, but kind of reasonable. We don't go crazy with compression and do weird stuff to don't reduce performance too much. But yeah, we would use less memory. If you specify no flags, we go automatically to the fast mode. And you can specify also a robust mode. In this mode, we use in this mode, we don't do some floating point optimizations that could mess up the quality of the intersection. So standard Muller-Trumbo intersection, for instance, has a lot of problems if you move, let's say, a tessellated sphere 10,000 units away of the origin. If you look onto this object, it looks pretty crappy and has many holes. So we have in this robust mode an algorithm that can even handle this case in single precision floating point robustly without producing cracks. As I said, so it's something like over 120 million triangles per second. If we come to the boost, I think we can compute the numbers there live with this 2 million. Because we have there on the demos the milliseconds printed out, we can just do the math there and tell you exactly what the performance is. But over 100 million primitives per second is easily possible on modern machines. Okay. if there are no questions anymore, maybe a final question if somebody wants. Otherwise, we close then. Okay, then thanks a lot for your attention.
Is this position okay for the microphone?
Yeah, just judging by how you can hear it.
Well, it sounds fine up here. Okay, great.
If everyone can hear you, you're good.
So I just noticed a minor omission. I forgot to put my name up in the title of the slides, but my name is Carson Brownlee. I'm part of the software ray tracing group here at Intel as part of SDViz. I'm officially part of the Osprey team here. Osprey is this is going to be kind of an extension of the previous talk because Osprey is a rendering engine built on top of Embry, our ray tracing kernels. So a brief outline, there's quite a bit here to cover. Osprey was originally intended for SciViz, but we support photorealistic rendering, distributed rendering, display walls. There's quite a few things to cover. I'll give a brief overview of Osprey introduction and a refresher. Osprey 1.0 was officially released a year ago now, or just over a year ago. 1.0 was released in June of last year. I'll be going over some brief API syntax as well as kind of a brief how-to overview of the library, as well as how to extend it and how our module interface works. I'll go over what's changed in the past year. I'll go over our MPI interface. From previous last year, we now support not only replicated scenes, but also data distributed scenes, as well as prototypical in situ interface. I'll be going over how to extend it yourself briefly, as well as coming additions to Osprey. So for a brief recap, Osprey stands for the Open Scalable Portable Ray Trace Based Rendering Library. It's open source on the Apache 2 license. You can download it at www.osprey.org. This is a fully open source project. You're welcome to download it, use it however you'd like, and extend it, and hopefully contribute code back. We are very open and very much appreciate contributions from our community. We are, just like Embry, we utilize Embry internally, and we are a fully CPU-based rendering library. Over our booth, we've gotten a lot of questions about GPUs, but we are in fact only run on CPUs. As part of the software-defined visualization effort, we include Embry, which is our open source ray tracing kernels, which Sven just covered in the previous talk. Osprey is built on top of Embry. We are a rendering library, so effectively you can take Osprey, which utilizes Embry. You specify your data, you specify your scene, materials, and you'll get an image back. So this is meant as kind of a turnkey solution for generating images. We also have what's called SWR, S-W-R. This is a software rasterization project. This is because we found that people using Mesa for software rasterization was a bit suboptimal. So we provide our own open source solution for that, which we also release, so you can find on the sdviz.org website. Osprey was originally built for scientific visualization, but it really applies to anything for which you might use ray tracing for. It is also designed to be highly extensible, so you can take the base optimized distributed rendering package and extend it to implement various renders, materials, geometries, and etc. We support Linux, Windows, and Macintosh. Binaries are available for many Linux distributions on our website. It is also pre-packaged currently with several other packages, other programs out there for scientific visualization, which we'll be going into later. So we support a lot of, so Embry, as Sven just mentioned, supports custom geometry types, and we've went ahead and utilized that to support many types that will be necessary for specifically scientific visualization. This includes regular grids for volume rendering. We provide a volume render with pre-negation, adaptive sampling, surface shading. Recently, we have prototypes that we have not released yet, support for AMR and unstructured volumes as well. We support implicit isosurfacing, so instead of generating a triangle soup to represent an ISO surface and a volume. We can generate that on the fly during render time. We, of course, support triangle meshes, tetrahedral meshes, hexahedral meshes, AMAR data, though it's not been officially released yet. We support streamlines, spheres, cylinders, as well as custom geometry types. So if you would like to take Osprey and extend it to support whatever function you would like to implement, that is easily extensible and can tie into our existing shading operations. It's built on Embry, as I mentioned, which gives us great performance on CPUs. You can go down to our booth and see our utilizing the path tracer in Osprey, as well as the volume rendering basically in real time. This is for the train model. We were seeing around 30 to 80 frames a second. And then for we also show it rendering in pair view interactively with a large 200 gigabyte volume. Osprey is pretty broad industry support right now, at least in the scientific visualization realm. PairView is the most widely used open source visualization package out there. It's meant for general visualization, so it supports visualizations across many different domains. It has a wide range of data loaders, supports a wide range of formats. That in turn is built on VTK. We also have a VTK implementation, so you can utilize your VTK code, enable Osprey with effectively one line, and then use Osprey for rendering internally in PairView. We also have a prototype visit implementation. It's not nearly as fleshed out as PairView, but it is available for those that wish to try it out. We have many users as well, everyone from universities to NASA. Really, if you go to supercomputing and just walk around, you'll either find people generally all over the show floor either using our stuff directly and showing it off, or indirectly we can sort of see images that we're likely utilizing Osprey. So we've got quite a few partners. Brief timeline. So Osprey was first released a little over a year ago, June of last year. Since then, there have been quite a few changes. We have added vastly improved volume rendering. So before it was direct ray casting only. It now supports surface shading, ambient occlusion. You can get volumetric shadows, and it's also considerably faster. We've added pre-integration and adaptive sampling to it. Stereo rendering has been implemented. We've got a notion of Osprey devices to isolate our code bases from local devices to MPI devices to data distributed devices. We support normal maps, emissive materials. We have a basic in situ interface now where we can support data distributed volumes and even now geometry. We also support latest Skylake processors. In upcoming releases, we'll have unstructured and AMAR data support for volume rendering, as well as we're planning full support for in situ, which is a major priority for us. So Osprey can do a lot of things. Scalable image quality. So on the bottom there, we see a perhaps overused image, but we have direct ray casting, basically rendering in PairView to mimic what OpenGL will look like. It's without any advanced features. This is just all local lighting. We can get real-time rates with fairly large data sets, basically up to as much memory as you can throw at it. We can get interactive rates. And then you can scale up that rendering quality inside of PairView itself. Here is a path-traced image shown on the right. And you can scale up that performance by scaling the number of samples per pixel, the number of bounces, and whether or not you're using our SciViz or our photorealistic path tracer renderer. We also scale well with model sizes. We've run terabyte size volume data and billions of triangles on large systems. So we scale from a laptop up to thousands of nodes on a compute cluster. And we also support display walls. Up in the top right is shown TAC's display wall. I believe it's around 300 million pixels being rendered interactively. So we have two different renders right now, and SciViz render is actually a new advancement from last year. Before, we had renders very much tuned to specific tasks. We had one render for volume rendering and then one render for fast triangles and things like that. But now we only have two renders that do most operations. SciViz is intended for fast real-time rendering for basic SciViz rendering, so local illumination, but also supporting ambient occlusion and shadows. So this is typically something that you might use for interactive scientific visualization, where you want sort of locality information, being able to tell where streamlines are in relation to each other and things like that. It also has our volume render. Our path tracer is meant for photorealistic global illumination. It's a full brute force path tracer, no radiance caching. We don't even have a denoiser in there right now, but if you come down to our booth, you can see it is quite fast and quite usable. So the vision is you take the same data set, they can run on your laptop or workstation, and you can scale it up either in terms of data size or performance by running it on a cluster. So we have a notion of workers, which are, without having to build ParaView and run it on a compute cluster, you can just build our Osprey MPI workers, which have minimal dependencies, run them on your compute clusters, which connect to your display node, which have your GUI with ParaView and everything running, connect to that, and then stream them over to a display wall or back to your workstation. And this scales from a single node to thousands of nodes. And it scales from a single display to, I forget how many nodes or displays are on TAC, but at least dozens of displays. I believe it's about 80 displays in that case. So Osprey is officially released with ParaView now. If you download the binaries, it just comes with it. So you don't have to do anything more than that. If you build it yourself, I should say it's not enabled by default, but it is a CMake option. If you enable it in CMake, it is buildable directly from ParaView. So it's in the source and officially supported by Kitware. This is no longer a plugin that you have to download. It's not something that's going to break with recent versions of ParaView. This is something that's maintained by Kitware itself. So as an example, this is a volume rendering done in ParaView. This was shown at last year's supercomputing. This is showing a brain tumor. This is both combining two different volumes with geometry used to show the slicing planes. And this is a volume rendering that supports ambient occlusion and shadows. You can see the shadows on the plane there. So these are advanced lighting effects, and this was running about 20 frames a second on a small scale ZN5 cluster we had there at supercomputing. But it also just runs on a workstation a bit slower. So the more nodes you throw at it, the faster it's going to go. But this is running with, I think this was about 6 ambient occlusion samples per pixel and about 2 samples per pixel in addition. So that's a pretty good workload for a volumetric data set, but we can render it almost real time. This is an example of a rendering done by NASA Ames. This was a rendering done on their Viswald cluster. This was done by the team, Tim Sandstrom, as well as Inga Wald, who visited there. And by the way, at supercomputing, they had a great series of videos, many of which utilize Osprey. So I'd highly recommend checking out a booth the next time you're there. We've also been working with the Stephen Hawking Center for Theoretical Cosmology at his anniversary or birthday party, 75th birthday party, just last, well, actually, let's see, It's around July 4th. I guess which was last month now. They were showing during his presentation a video we put together in conjunction with that team. This is showing off a rendering done in pair view using our AMR volume rendering method, which is soon to be released. So this is not resampled into a grid. This is not projected TETs. This is a volume rendering that has been raycast and directly sampled the AMR structure data itself. And we are able to render this interactively. Oh, this is a video, but these are PDFs, so I can't play it. So we'll just skip that. So to show just how kind of scale this can handle, this is a 10 terabyte data set run on a SGI UV machine, and we could run it interactively. So we scale easily from millions of triangles up to terabytes of data. This is a demonstration. This is a video we put together for ISC recently in conjunction with DKRZ. From their climate model simulation modelers from Germany. The full simulation is 200 time steps, 2 terabytes of total data loaded in memory in pair view. We have a version of it running downstairs now using 200 gigabytes, and you can see that on a single node it renders interactively and can play back the full, the subset of the time series that we have loaded in 200 gigabytes. So we support display walls. In this example of running on TAC's Rattler display wall, and you'll notice that this is a fully path traced scene, and we were able to render it, I believe it's 190 megapixels in total. These are 4K OLED displays, and this runs interactively. And it's pretty amazing to see in real life when you can just walk up to it and see like a tiny little knob on a desk upstairs. So in real life, it's quite impressive. I don't think the resolution of this projector really conveys that. So I'll briefly go over the API. Osprey offers a set of logical objects. These are things like geometry or frame buffers, volumes, cameras, renders, materials, models, and textures. And what happens is we operate on basically an object factory. So you can override geometry to be whatever custom type you want. You can also swap out renders. Everything is modular and can be overwritten with either replacements or customizations of existing types. So an example of this is we have a handle to an OSP object, so OSP camera. We call OSP new camera, which calls our object factory. And in this case, we're telling Osprey to release a perspective camera. There's also setting parameters on it. So this is our C syntax. We also have a C++ syntax and a soon-to-be-released SIGGRAPH syntax as well. But for now, I'll only cover the C syntax. The C++ interface is much the same, just without the set 3FV and etc. So you create an object, you set parameters on that object, and then we have a syntax known as, which we call commit. And when you commit an object, this is what will build whatever representation internally that we need in ISPC or whatever the backend is doing to make whatever changes are needed on the render. So this will, for instance, build acceleration structures in Embry. This will send data over the network, and commit is what basically makes that changes that you've made in parameters apply, basically. So a year ago, if you looked in our apps directory, Osprey itself is a library, but we come with several example apps. And a year ago, this was kind of a mess because we had different sample apps to demonstrate different things. So if you wanted to render a volume, you'd run something different than if you wanted to render a triangle soup. And the code was kind of, it was just a mess to work with, and it was confusing for users. So we finally unified that into a single example viewer. So if you look in our develop branch, and this will be coming up in our upcoming release, example viewer actually becomes our SIGGRAPH viewer. So we have one viewer to handle everything on Osprey right now. So this is just an example app, but it can render and manipulate properties of everything that Osprey currently supports that we want to demonstrate. So you can open the GUI, and you can, for example, you can even add lights from the GUI itself. You can manipulate light positions. Everything that's loaded and changed in Osprey in a SIGGRAPH is editable. So this comes in handy. In fact, you can set up some pretty complex scenes straight from the GUI. We also have integrations into mainline tools. We support PairView. There's a prototype in Visit and VMD, which is a molecular visualization software, and many, many more. So in PairView, like I said, it's built into the binaries. This is officially supported by Kitware, and this is a screenshot of it running, which we also have running in our booth. And if you look on the bottom left there, to enable Osprey, there's just a button that you click, enable Osprey. And because of the way it was implemented, you can switch between Osprey and OpenGL just by clicking the button. You don't have to change any other settings. It will reload it internally, but it doesn't have to like relaunch the program or anything. You don't need different separate displays like you need with a plugin. It's just click that button, and then your scene shows up rendered with Osprey. It also, as you see, the options are, we support shadows, ambient samples. So ambient samples of 0 is ambient occlusion is off. Samples per pixel is the number of samples we shoot per pixel. So in this case, 256 is a very high quality rendering. So it's pretty much fully converged, as there's no noise from the ambient samples. Progressive passes. So if you launch PairView with a special mode on the command line called Enable Streaming, it supports progressive refinement. So anytime you're not interacting with the camera, it will continuously render and get smoother and smoother over time. So I would highly recommend, if you're planning to use Osprey, always launch PairView with Enable Streaming enabled. This is not a well-known feature, unfortunately, but it is extremely useful for getting smooth images. We also have implementations in VMD. This was done by John Stone. We also have a prototype in Visit. I'll briefly go over performance comparisons. So this is really, really apples to oranges. And this is more of a ray tracing versus rasterization argument. But this is real-world performance. This is something that we got into PairView, and these are actual results you'll get today if you run these numbers. Osprey is open source. PairView is open source. You can download it and run these tests yourself today. Our website has demo apps you can download and time yourself. So in this example, we're running a Titan X card to do rasterization in PairView. And this is comparison against a dual socket system running our CPU ray tracer. So when you're running just a few triangles, a moderate sized data set, let's say this one's around 10 million triangles, the GPU is getting nearly 80 frames a second, and our ray tracer is getting about 35 frames per second at 1 megapixel. However, as we go up to 660 million triangles in the last example there, you'll notice that our performance has dropped around 25 frames a second, so it scales very well with increasing triangle counts. And in this case, the GPU actually crashed inside of PairView, or I should say PairView crashed running the GPU at that kind of scale. So you can see the trade-off is somewhere around 90 million triangles where those two renders become equivalent. So in all cases, our render is highly interactive. So if you're looking at large data, you can interact with it from 10 million up to pretty much however much your system can fit. Like I showed before, we've rendered up to 10 terabytes on a single UV machine. So our two renders, this is showing the SciViz render. Examples here, we're using ambient occlusion, we have shadows, transparencies, we support volume rendering. The bottom one is actually a volume rendering with a gradient shading enabled, so it looks kind of like a surface. And the volume rendering, as you can see, supports shadows and ambient occlusion. And this is inside of ParaView. So the standard ParaView volume render won't support any of these features. But we can do that all on the CPU interactively. This is a high-res image of the Cosmos run that was shown at ISC. So an overview of the new features. We actually just released our data distributed geometry and volume rendering. So if your data is chunked up over many nodes and you don't have it all resident, you can now specify distributed volumes and distributed geometry to render. There's no need to replicate the scene to render fully. This was already working within ParaView using their own compositing, but now we support it using our own compositing and get pretty good performance. Since a year ago, we've gotten roughly 50% speed up for volume rendering. However, it's really anywhere from similar speed to 10 to 100 times faster, entirely depending on what you're doing. New tasking systems support, primarily we use TBB for threading now. We've got pre-integration in our transfer functions, adaptive sampling for our volumes. We've released OSP Common, which is kind of common SDK features for our math libraries and whatnot that you can use. We have a C++ wrappers for the API. Binary releases, we maintain binary releases with every new Osprey release. We also have explicit benchmarking tools, so you can download our demos and run your own benchmarks to validate our numbers. The new volume rendering features, full shading with shadows and AO, adaptive sampling, and pre-integration. And these are really what got us up to, in some cases, 100x speed up over when using gradient shading, especially for volume rendering. So now, volume rendering with gradient shading used to take, it was sub-interactive, basically. And now it's fully real-time in many cases. So as an example, this is direct ray casting with the volume render, and this is with shadows and ambient occlusion. And you can see it makes a fairly dramatic difference. And this is still done interactively on a single workstation. For MPI, we support both shared memory systems. In this case, this was run on a 3 terabyte system, and this is showing billions and billions of spheres. If you look in the zoom in section, each of those points is a tiny implicit sphere that's been rendered. We also support distributed memory systems. The data set shown is a DNS simulation, and it's about a terabyte in size that we've run at TAX supercomputer, and this was running interactively. So the main reasons to use MPI are when your data exceeds the memory limitations of a single node. If you're running a terabyte size data set and you can't support that on a single workstation, because not everyone has a 3 terabyte workstation, then we can launch it on Stampede or some supercomputer distributed across nodes. and still get interactive performance. We do our own compositing of tiles. You can also get performance limitations. So whether you're distributing the data or replicating it, if you want to go ahead and replicate it and you just want faster running performance, we scale extremely well with replicated scenes. So the demos we have downstairs running right now are using data replication to scale across 8 KNL nodes, and we can get real-time path tracing performance. Tile displays, so we run on hundreds of megapixels tile displays interactively, and we can only do that using MPI. Also in situ rendering, so if you're running a simulation software and you want to render while your simulation is loaded in memory, it's distributed across 100 nodes. Instead of having to process that in some fashion, you can take it directly on the distributed run and render right on the node. Strong scaling, this is demonstrating volume rendering that was done on TAC Stampede cluster, and we achieved a throughput of up to 180 frames per second running on 128 nodes. So we do limit around, it drops down to 100 frames a second or so at 256 nodes, but 100 frames per second at 256 nodes is quite good. So aside from strong scaling, we also do pretty well for weak scaling. So this is we scaled up a path traced image rendered in pair view. So for each node we added a sample per pixel. So on the left is one worker, or one node in this case, rendering at 1 sample per pixel at 4 frames a second. And when we run that same thing at 256 samples per pixel on 256 nodes of Stampede, we render it at 1.42 frames per second. So we're rendering at 256 samples per pixel interactive. And it's quite a thing to see, a fully converged rendering that you can spin around. I'll quickly go over our new data distributed device. So we have a notion of devices in Osprey. This is things like when we're running it locally, when running it MPI replicated, or MPI distributed in this case. We create a volume, we set data locally, and then set that data, and then internally our implementation will communicate with each other. So they'll figure out the bounds of all the nodes in the scene and then composite accordingly to get the resulting image. So from the applications developer standpoint, when you're running a simulation, all you really need to know is send it your local data, and Osprey will do the rest to composite it correctly. To use MPI, we have a CMake option that you need to enable in Osprey when building. You need to enable the MPI distributed support in MPI as well. So there's 2 options you need to enable. To run it, excuse me. So this is running, the first example is running with 3 workers in MPI mode using a Teapot scene. So this will basically take the host node, the first process 0, and make that the master rank process, and then it will automatically take over the other processes and make those into workers for you. Workers are what take jobs and run them remotely on the other cluster nodes or other processes. In the other example, we have Intel MPI supports a notion of like a hybrid run. So the first process in this example is running our display. So as you can see, we specify on the local host, we're going to run our GUI, the OSP example viewer. And then for the rest of the processes, we'll run the Osprey MPI worker. And now this is important because when you're running on a compute cluster and you want to run, for example, pair view, now this running mode is actually currently supported in pair view. So what you can do is build pair view or download the binaries on a head node that has a GPU and a display and all the dependencies that pair view has. And then you could run pair view on process 0 and then run MPI worker on the other compute nodes and then use them for rendering. Osprey MPI worker has very limited dependencies. So you don't need to put all the libraries that you need for pair view onto your compute nodes. You just need to put the Osprey dependencies, which are very limited. And the last example there is using just the same run syntax inside of pair view itself. So pair view has no notion that it's running distributed in this case. Everything is handled by Osprey. It just runs, think it's running on a single node, and then internally Osprey uses the Osprey workers that you specified after the colon on whatever host you specified to run externally. The distributed frame buffer, we support data replicated and data distributed. It has it uses a tiling syntax, so if you're using data replicated, it'll send individual image space tiles to each of the nodes. In the case of data distributed, these tiles, it's a similar syntax except that it figures out the bounds of the local data and then composites them together. So there is some overhead there. It will scale much better if you're using pure image parallel distribution with no compositing. So when you have the memory for it, it's almost always better to use data replicated and then only use data distributed when you can't fit it into resident memory because there will be a compositing overhead. You can also specify pixel operations to be done distributed as well. For example, our display wall code to render and send tiles to individual displays on the display wall, that is all handled through custom pixel operations. And this could be anything from filter operations that you can specify manually, and it will all be done distributed effectively for you. So the display wall is currently experimental, is available as a module. So please contact us if you are interested in utilizing that. I won't go much more into it now, but we'll be officially releasing it soon, I hope. To utilize it, you can specify a head node or no head node, and what that means is if your display walls are typically connected to a cluster where there's a server hosting each or one or two displays, I should say, and it's not always the case that those nodes can actually contact what you're rendering on. So at the case of TAC, we might be using 1,000 nodes of a supercomputer to render, and we want to stream those to the nodes for the display wall. However, because of the network configurations, the nodes on the compute clusters are not always accessible to each of the nodes on the display wall, so we have a notion of a head node where you can pipe all the communication through the head node if necessary. A brief overview of performance, just to compare KNL versus a dual socket Xeon. And you can see that a dual socket Xeon is roughly comparable to a single KNL node for many of the scenes we tested here. This is kind of just a scattering of the scenes that are available on our demo page on our website. They can go and download today. And here you can see a similar story for 2 megapixels versus 1 megapixels. So Osprey was designed from the ground up to be extensible. So we want you guys to go take our rendering code, implement your own renders, your own shaders, your own cameras. We've had people add custom. We have a stereoscopic camera, but we've had people implement their own 360-degree view cameras and things like that. You can implement your own shaders, custom geometry, intersections, and everything that you can create for the most part is fully extensible. So to give a quick example of creating a module, we have a notion of Osprey modules, and these tie into our object factory. So in this example, we'll create a multi-hit module. Multi-hit is, well, this is just an example, but multi-hit, this is for a paper where instead of doing a single intersection, figuring out if it's transparent, doing another intersection of things behind it, we gather all the hits along array, put that into a buffer, and then we can utilize that without having to retraverse the scene after an intersection. But for this example, here's the CMake code needed to make a module. We enable the option in CMake. We have custom functions in CMake to make your life easier. This is for creating a library or an application to run it in our example apps. So you just need to specify your source code that tie into our existing code base. It does need to have a specific naming syntax. So this is when you call OSP load, it will figure out the correct naming syntax for that. So we use CMake for all of our builds. So like in ParaView, it just calls find package, and we set up all the dependencies for us. And a note that please do not depend on our sample code because it's often changing. We've had many people that copy and paste our sample code, which is really just an example, and then they complain when things break or change. That's our sample code is just an example of how to utilize the library, and it's highly in flux. So this is how to include Osprey in your code. Use find package Osprey, include, this configures ISA targets, and that's really all you need to add Osprey to your CMake code. So Osprey plus ParaView, we have standalone volume rendering support. This composites with OpenGL, so without enabling Osprey for geometry as well, if you just want to use Osprey for volume rendering, we support that. Whereas Osprey rendering mode renders everything with Osprey. We can match OpenGL with local lighting, so if you want the exact image you would normally get in ParaView, we can enable that, or you can add shadows in AO for advanced effects. Path tracing is also being worked on, but we have no official release date for that yet. We also have Catalyst support for in situ. Osprey already works within Catalyst. You can utilize that today. And coming soon, we have Path Tracer, AMR support, and unstructured. Go over a few performance tips real quick. Single MPI process per node is ideal. This is known as MPI hybrid parallelism. We do not want multiple MPI processes running with Osprey at all if it can be avoided. We can't support that. You can designate how many threads you want Osprey to utilize, but ideally you have a single MPI process per node. Excessive API calls can decrease load times in MPI because every call you make in the API needs to be broadcast. So if it's a few thousand calls, it's no problem. If it's millions of calls, that can be a little tricky. We have, since last year, implemented batching, so we can batch API calls together. This mitigates the problem, but doesn't entirely solve the problem. Affinity issues, we often run into affinity issues with MPI on clusters. So this basically pegs threads to specific cores, and what happens is we end up Osprey running on a single core on the system. So if you notice very low CPU utilization, make sure that affinity is off and that we're getting full thread utilization. For KNLs, we found that the best caching mode for the MCD RAM is in quadrant mode or quadrant cache mode. We didn't put specific code in for utilizing it in flat mode. We just found that cache mode for our cases works pretty well. For the samples of pixel, you can set the number of samples per pixel to be negative. And what this means is that for the initial frame, while you're interacting, it'll actually subsample the image. So effectively 1 pixel becomes 4, for instance, and -1. And you can don't have to, it doesn't stop at -1. You can -2 up to -10. And you could basically have the entire image rendered with one sample if you really wanted. There's also variance thresholding. So if different parts of your scene are converging much faster than others, say if your main object is noisy, very high frequency, then what will happen is the background will converge very quickly, and then basically all your rendering work is going towards the renders with the tiles with high variance. So if you enable the variance thresholding, which is off by default, to a tolerable level, then the background pixels will stop rendering, and then all the work is being focused on areas of high variance in your scene. So brief overview of what's coming. We're working on additional in situ support, new Embry features, quad meshes, Bezier curves, race streams, performance gains, upcoming AMR volumes, unstructured volumes, cameras, and we've had multiple requests for volume instancing, which is coming, I promise. And this is really more of a plea. If you make modifications to Osprey, please send them back to us. We love it when people send us their code and their modifications. For more information, please visit osprey.org. And any questions? Yes? Well, right now, so we have no notion of multiple, like we don't import and sample lights. So it'll iterate through the lights. So yeah, if you have like 100,000 lights, that will be slow. We will import and sample them. I've heard that's forthcoming. You can self-manage them yourself right now if just selecting ones that are local. But yes, if you have 100,000 lights in your scene, that's going to make a significant performance decrease. Any other questions? Yes, Ben? Mm-hmm. Uh-huh. Right, well, this is known as weak scaling, so it's like perfectly, if it was perfectly scaling, you'd be seeing the same frame rate, right? But this is kind of showing the overhead of our well, it's probably related more than anything to the lack of a dynamic load balancer in there right now. Which actually, we recently did put a dynamic load balance in there. It's just not on by default, and it wasn't available when this was done. But still, I mean, 256 nodes and running interactively with 256 samples per pixel, it is not perfect scaling, but that's pretty decent. It's still scaling up with more nodes thrown at it. Any other questions? I'm gonna let you guys go home. Or go to the Pixar party over here. Thank you.